you come by and replace it? I think he did. Let's see if this is the mic. Test, test, test. Yep, this is perfect. So this is much better. And let's just, we'll test it on you if you want to wear it. That way. Test, 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 test. Okay. I want you to try it. And how do you pronounce your name? Gerardo? Gerardo. Gerardo. Okay. Okay. All right, Gerardo. I want you to try it. I'm gonna see if I can put it on your. See which way. This way. This is better.
Probably Fabricio will use this, but I will try it.
Okay.
Testing, testing.
Nope.
Nope.
So you probably just have to hold it like this and talk. Okay.
Maybe here and
Yeah, that's it. So,
okay.
See.
Testing, testing. 1, 2, 2. 1, 2, 3. 1, 2, 3. It is a testing.
Yeah, you're good now. We're just waiting for a few more folks to trickle in, and then we'll get started. All right, I think we're going to get started. I'll give just a quick intro on our speakers who will be talking about Cilium and observability. We've got Gerardo Lopez Falcon and Fabrizio Segura. I hope I didn't butcher the names. Gerardo is a Google developer engineer, and he's based out of the beautiful Costa Rica. He's also organizer of a cloud native Costa Rica, as well as KCD Costa Rica. And cloud native applications. He's into about blockchain technology, cold chain, and pharma apps. So without further ado.
Hello, people. Good afternoon. I want to be closer to you, so I will be there. So nice to meet you again. It's a big pleasure to be here. Thanks for coming. How many of you has experience with Kubernetes? I see the faces. I see sad faces. I don't know. Yes. No. I hope that this session is useful for you. So today we want to explain what is Elevate Security and Observability with Cilium. It is the agenda. A little bit about eBPF, what is Cilium, how or what technology we can use in order to set up the environment and start to troubleshoot Cilium. A couple of demos, Cilium Observability and Cilium Security. So we are, again, Gerardo Lopez. It's a big pleasure to be here. In the next slide. I'm a principal engineer in Veritas Automata, super fan of soccer, movie, barbecue, and my colleague, Fabrizio Segura, chief engineer. So again, very happy for this chance. Okay, thank you. So let me explain a little context. In today's landscape, all about Kubernetes microservices is a big topic, focusing on networking, on security, and of course, network observability in Kubernetes is a paramount due to the growth exponential usability and usage in production environments thanks to Kubernetes, okay? So the higher-end complexity of distributed architecture right now is causing that we need to pay attention to different things. First of all, performance issues. Second one, we need to pay attention about possible vulnerabilities. So it is the reason that we need to enhance security and improve observability. Why? Because allow us identifying and mitigating possible vulnerabilities and performance issues as well. Proactively, we can detect and resolve network and performance issues. And lastly, this contributes to maintaining the integrity, reliability, visibility, and availability of application deployed on Kubernetes. So again, work on distributed architecture is a big challenge. It's beautiful, you can have different things, but we have challenges to resolve in the backbone, the network. So in the next slide, we can explain the main topics that we are using, and why not? You can involve with us in this adventure. So what the ePF is? What ePF is an interesting technology. It's an open source and flexible framework that, in simple words, you can insert dynamically snippets or code into the Linux kernel space using a way and secure manner. So you don't need to modify the kernel at all. You add dynamically and runtime the code and add new functionalities, in simple words. Overall, ePF is a versatile technology that empowers developers and administrators to extend and enhance these skills or these capabilities in Linux kernel in a safe and efficient manner, opening up a new possibilities for performance optimization, observability, and of course, security informants. Different use cases. In the next slide, we can see about how the business or different use cases the people are using about ePF. So we can start about 3 important pillars that we believe all application needs to have. First of all, the networking. So it's very important. Right now, there are people, other project, open source project and private project that is incorporating network policies, enforcing the network, and of course, the security itself. So networking, security, and observability and tracing, 4 and 3 pillars, very important that ePF is doing into the cloud-native ecosystem. So if we go to user space, you will see we have project and SDKs. So most important project, of course, PC. You can continue creating code thanks to PC and incorporate or add into the kernel. Cilium, Falco, Catran, and Pixie. Of course, there are a lot of other projects that we can use, but if you see right now in the cloud system or the cloud architecture native, you will see this project the people are using. So about the SDK, we have, I think, so important range of technologies. How many of you has experience using Golang? C++? Yeah, it's normal, no problem. C++. Of course, Rust. Okay, Rust. So right now, there are the SDK that ePF has. Why? It's totally normal, because this programming language are more focused to the low level. So for this reason, different SDKs. And probably in the next years, new programming languages will appear in this list. Of course, we can optimize the application using tracing, profiling, and monitoring. So about the kernel runtime, we can see we can use technology like verifier, mapping, and others. So again, observability is not the same than monitoring. Thanks to observability, we can go beyond. Why? Thanks to ePF and Cilium and this kind of technologies, we can make decisions. What make decisions? Why? Because if you don't have metrics, if you don't have measurements, how you can make decisions? It's hard. So I need data, I need measurements in order to make decisions. So ePF, in the next slide, thanks to ePF, appears new technologies like Cilium. Cilium is a powerful networking and security solution for Kubernetes environments. And so regularly, you will see that people say, Cilium, Cilium is another CNI. Cilium is not another CNI. Why? for all the capabilities that Cilium offers. So we can probably discuss Cilium versus Calico, Cilium versus Flannel. We can this later in the coffee in order to continue with the presentation. Or if we have time, we can discuss a little bit. But Cilium go beyond to the CNI. Why? Because Cilium offers advanced feature in the layer 7. So it means that we can capture metrics, flow in the layer 7 and layer 4. So it's a great thing because you can capture all the flow that what is happening in the network. By leveraging eBPF technology, Cilium provides efficient packet processing and scalability while ensuring robust network security and observability. It enhances Kubernetes networking capabilities, enabling seamless communication between microservices while enforcing security policies and SCaLE. So we have all in one. We can improve security, observability, and of course, all related with the monitoring stuff. A little explanation, high level, how Cilium works. It's totally common. It's the fact right now in Kubernetes environments, different applications are using the operator. The operator is responsible for managing all the concepts. Cilium has the operator, and thanks to the operator, can communicate with all the nodes. Cilium, using the approach daemon set, it means that in all different nodes in Kubernetes, install an agent. It means this agent is responsible for create and monitor the networking communication between pods into the node. So it means that if I have 10 nodes, I will have 10 agents. And responsible for maintaining and updating all the life cycle of Cilium is the operator. How the operator communicate with the agent using the key value communication. So similar with the ATCD in Kubernetes, it is the communication that is happening. It is a little bit high-level architecture about Cilium. Two important components, operator and the agents. In the next slide, we can see all the advantages that we can use in Cilium. Network visibility, service discovery, rich metrics. I will see example in a couple of minutes how we can get metrics from the kernel thanks to eBPF and expose in Grafana. So thanks to the rich metrics. With these metrics, again, we can make decisions. How is the performance of our application? How it is performing about our network? Layer 7 visibility, and of course, flow visualization. I don't know in your case, but in my case, sometimes I see developers that need more tools in order to see what is happening behind the scenes, because Kubernetes is a complex concept. So Cilium offers UI, interesting service map UI that I will explain it to you in a couple of minutes, and the developers can make decisions, can see what is happening in between different components. In the next slide, so it is other high level how Cilium works in this case. Cilium intercepts all the traffic, all the network traffic that is happening behind the scenes between our application, or apps, or pods, and create tools for us. Tools like Service Map, Hubble UI, in order that the people can see easier what is happening in the network. So it is a little diagram, in order, I hope that we can explain this. But Cilium is the heart, is the backbone. It's getting the information and creating for us. Okay, in the next slide, I will move to the terminal. So, in the meantime, my colleague Fabrizio will help me to create the environment. So, we want to recommend two technologies. First of all, if you want to work locally, you can use Kind. Kind is a good tool in order to create Kubernetes in your computer. Kind use Docker in order to simulate the nodes in your computer. It's so beautiful. So in this case, we are right now adding different images in order to work that. And the second technology is, we are not getting any promotion to say that, Rancher. So Rancher use RKey2. RKey2 is a good technology because you can specify in a YAML what CNI you want to use previous to create the container, sorry, the cluster itself. So, okay, let me get started with the demo. We have this script. If you see, bless you. If you see under the networking, we are disabling the default CNI from kind. We are passing or putting the true value. It means that we want to create a cluster with 3 nodes, 1 node. You can create. We can create 3 nodes. One node is the control plane. The E2 nodes are worker. But the idea with this example is create a cluster, Kubernetes cluster, disabling the CNI. We execute. No problem about that, because at finishing the activity, we can pass you all the scripts if you want to run in your local. Right now, we're creating the control plane. We're installing the storage class and joining the worker nodes into the computer, and waiting a little bit what will happen. It's, of course, we'll create a cluster so quick with that. So if we clear the screen, so we will add it, or we'll add all the different image versions, preview version. Why? Because the idea, in order to respect the demo, we need to accelerate that. A beautiful thing of kind is that you can reload images previous into the technology. It means that when you create things, the nodes will use the preloaded images and will create the things so quick. Right now, we are exposing or viewing the YAML that the cluster created. And so, waiting a little bit. All the images are preloaded into the kind cluster. And so what does it mean? It means that in the next script, we will create, right now here, exactly, thanks Fabrizio. So if we run kubectl get nodes, you will see that the 3 nodes are not ready status. Why? Because it's pending the installation of the CNI. If you see the pods, no any pods about Cilium. So then all is pending, of course, mainly the core DNS, because core DNS needs the CNI in order to work. So in the next command, okay, Cilium status, Cilium has a CLI. It's beautiful, because thanks to CLI, you can create and run commands behind the scenes, communicate with the cluster, and you will see what is the status of the Cilium. In this case, errors, of course, because nothing is installed. In this command, we will install Cilium. Cilium, you can install Cilium so easy using a Helm chart. Right now, we're enabling the basic features about Cilium. We run the command, and thanks to the previous preloaded images, this configuration will be so fast. What is happening behind the scenes is happening. Maybe you can run other commands in order to see, get notes. Yeah, right. If you run the command, you will see the start ready. Thanks that all the nodes are ready to use. If you run the command again, the get pods, you will see we have 3 pods, 4 pods, Cilium with dash some specifically definition. If you please run with the dash O wide in order to see what node. Wide, W-E, okay. Okay, Cilium status, you will see. Can you go up, please, in order to see the Cilium status? Okay. If you see, or run again, clear, please, and Cilium status again. If you see, okay, right now Cilium is okay, the operator is okay, different add-ons are not installed. For example, whole relay that my colleague will enable very soon. But important things, deployment, the Cilium operator, desired, ready, and available pods. Cilium is checking that right now the operator has installed 2 pods. Daemon said the Cilium desired 3. Why? Do you remember that I mentioned at the beginning why install 3 pods about Cilium, the Cilium? What is the answer? Why? Daemon said. Appreciate. Excellent. Thanks to Daemon said we have 3 nodes, and we install it 1 per node. And that's it. It's Cilium operator, we can see all the information, Helm chart, image versions, and that's it. So it's so easy to use, but of course, it is the beginning. My colleague will explain more about observability and security, and so, Fabricio.
I will run commands, because I like to do that, and I know that you like to see. So I will use this ice cream. I hope that you hear me. Can you? Yes? So we installed the kind cluster. Now it's time to go for setting some Prometheus, Grafana. What we will do, we'll create dashboards or show dashboards that we previously installed because Cilium is instrumented for observability. So at this time, like Gerardo started with the cluster, I am going to add more commands. And for this, I will comment this Helm command that will install initially the Prometheus Grafana. We have a gist here that is in our repo. All of the scripts that I'm using here, they are available in a repo that we are going to share with you as soon as you add us to your LinkedIn, because there is a price to pay. So, and it's shareable, so it's a gist that we have. Everything is working. Basically, the 00 are the scripts that are installing all the kinds and similar. It's ready to use. It's something that is working almost perfectly. So I will run that 03 script, then I will run this one. I'm using a modified version to show you colors. But basically, this other command that is enabling the relay for the Hubble UI, so you will see that we can instrument and see in the dashboards and in Hubble UI things that are happening. The idea is to install this Prometheus stack, so it will use the content of the previous script that I showed you, and then the enabling the service map, that will be something we will use to see the output in Hubble. After completing this part that is related to the service map, we can port forward the Grafana. I will just show you that the pod should be running here, otherwise we fail something. In the monitoring namespace down there, there are Grafana and Prometheus available, so we have our observability embedded in kind. That is always a good point to learn how these tools are working. So we installed both Prometheus and the service map. Now it's time to do something that is the port forward of Grafana. We can see that here I have the command ready to gain time, but basically we are going to expose the service endpoint that Grafana is creating with a port forward on the same port 3000. I left that for visibility. It can be omitted, but really it's something that everyone will appreciate. And I should be able to run a browser somewhere. Let me check if I can find the browser to have it on port 3000 and share with you the output of Grafana as we prepared previously. So I'm going to put Grafana here. There is no trick. It's really the Grafana that I installed. As you can see, it's running on localhost 3000. And we will see that we already have tools that are able to provide us some metrics. So if we go here, this is already embedded in Cilium. So you don't have to bother about building your dashboards, querying the data, just installing Prometheus and sending everything. We can scroll down. Probably it's not really readable at the moment, but there is a lot of metrics related to eBPF, to the network itself, and many other informations that can really be useful when you are troubleshooting and you are being not just a DevOps, but also whatever you are doing with the CNI, eBPF, whatever. As you can see, it's a lot of data. You just have to get familiar with that, and it could really surprise you. A part of the Cilium metrics that we have here, there are other dashboards related to the Hubble UI. We will see that the UI is something that is coming on after running a command. And you see, it's very useful. So I will not enter the detail of all the dashboards that we have here, but as soon as we use the stack that we created, it will be filled up with a lot of information that are obviously very important for each one that is working on this kind of detection. So if we come back here, now it's time to expose the Cilium Hubble UI. I will use the typical Cilium Hubble UI command because it's probably the faster one that we can use. So I will switch terminal here. Cilium Hubble UI. It should open something if I have no typos. No, it's okay. I will share with you the screen of what it opens. So it's a primitive interface. They are working to improve the content here, but basically we have all the namespaces that we can query. And here you will see that there are the components that are running and a status that is interesting because we will see in the next section that is related to security. I will be very brief on security because we can do a lot of things with the rules that you can use for layer 7. What? Yeah. So I can enhance the screen, but it's not something that you can view more. I can do the Control+, but I think that really it's something that you can experiment downloading the scripts. So the content here basically of the Hubble UI is giving us a situation of what is happening across the pods that are running inside the cluster. Are you familiar with Hubble? Someone that is familiar? No one is familiar, so you are. Cilium generally started with Hubble embedded. It was the initial idea for giving visibility to all the things that were happening among the different pods running inside the Kubernetes network. At that point, they didn't enhance that a lot, but it's still a valid option to filter out what is happening in the column where you see the green. When we will run the commands to query a specific rule that will be forbidden, you will see that there will be a red one, or we can also use the Hubble observe command using the Hubble CLI, but for the moment, let's leave it as it is. And let's go for installing a pod. Now I will be using another one, so this one, and I will install a pod that is just running Nginx. Oh, pod. So let's see what it is. These pods, this script, is just installing the classic pods that you have in the Kubernetes documentation. I kept it easy to read for that reason. And I will also use a policy. Initially, let's go for the Kubernetes one, this one. So if you are familiar with network policies in Kubernetes, you see that here I'm using a classic easy one, so I am just saying that I'm allowing ports 80 and 443, and I'm also allowing DNS traffic. The difference that I want to show you at level 7, it's very simple, basic. You can do much more things with rules on the HTTP level. So in example, you can filter on Nginx the route to a specific page. If you have the index.html and you want to see it, but not the about.html from specific filters that are related to labels or annotations or other strategies that you can find in the Cilium documentation related to the rules, it's really flexible. What you can do in Cilium, you cannot do in Kubernetes policies. So if we use this, let me see, because I don't see what I'm writing. So, tickets, Cilium, policies, YAML, yes. This is the difference. As you can see here down, I'm specifying only the endpoint of google.com that is queryable by the DNS. So after the testing, we will not be able from that container to run a query to another endpoint. That means that I will be able to filter at level 7 the application layer for querying a specific DNS without blacklisting it in another way. This is not possible in network policies, so it's a big difference. As I said, you can do that on the HTTP level. You can see here that there is a specific DNS reference in the list of YAML. I hope that you can see the characters, but probably not. Let's see if I can get bigger. Not that much, but I want to show you a specific entry that is describing the ability of using the kubedns for that port, and down here you can see that we have the DNS entry here. So I can specify the effective name of the endpoint that I want to query. Now we created the pods of Nginx. So what I will do is run in a couple of commands. But before of doing that, I will show you the commands. So we will use the classic Google is responding, and we will also query another endpoint that is familiar to everyone. We will use Microsoft. It is responding. At this point, I will apply the Kubernetes policies. Nothing will change. It's the same policy translated to Cilium later. So I'm applying that policy that was the first one that I showed you. And you will see that Google will answer, Microsoft will answer too. Now let's delete the Kubernetes policy. So I can use my specific command line. Oh, yeah. We deleted that one, and we apply now the other policy that is the Cilium policy, NS, because it's based on namespace. I forgot to comment that this policy is a specific of the pods that I'm using for Nginx here. So it's a pod called HTTP test namespace and Web Nginx pods. At this point, I will run again the two queries, one to Google. You remember that should work. And, oh, not answering. But look at the message. It's not a curl appending. It's a cannot resolve host. So it is acting exactly on kubedns. It is not resolving for that specific host. Saying that, we could look at the browser where we have these specific entries. And here we see that in this case, it is still forwarding. Probably I need to refresh this. Or maybe I will use the Hubble UI, the Hubble observe command, because for this specific thing, we will be able to see a red login line. So let's go here. Red login line, let's see. Now, you see that here it's full of green forwarded messages. If I go to call again the commands that we were using previously, so I should have them saved in this terminal, I can use them. No, I will open another terminal. It's a little bit. And I will run the 2 curl that you saw earlier. After some time, here, it should not show, it should show something that is traced. So not forwarded anymore, but traced by something that is in color of brown. That means that the behavior is not forwarded anymore, but it's sent to trace because it's observed in the previous dashboards. All the things that we did now are available, obviously, in the Grafana interface. That should be still available here down, or here. And we should be able to see a lot of information related to the tracing and the activity that we did on the Cilium metrics and capture. You can see that data has been filling for all the time that we were effectively running commands, and it's confirming that we can observe what is happening on the network. So saying that, I think that we completed the part related to the operational demo. We can come back to the slides, skip the part related to the black boxes here, but I would like to focus to one point. So how you can do to create these Cilium policies for network. I've been using the editor that is available online by Isovalent. You can go to the page and you will see this is not something that you can run locally as far as I know. I've not been able to do that, but on the site of the Isovalent company, you can run this specific interface, a page, and create your own rules. They will be available here as a Kubernetes policy, network policy, and as a Cilium network policy. So I decided to include what was the same YAML files that I used and I generated here. As you can see that in this case, it's very visible and easy to use. If you go there and you are familiar a little with the namespaces, the isolation, and similar, this will produce an output here down that you can copy paste in your cluster and do the same experiment. I think that is everything that I can share with you for today, and go ahead with adding specific things. So Gerardo, I will give you the ice cream.
Thanks, Fab. Before go to the questions, I hope that probably there are. So Cilium is very proud to say that Sidecarless. Sidecar is a good pattern that regularly, I like it, no problem about that, but the pattern of Sidecar is add an extra pod, one specific pod for example, proxy or collecting things, irregularly the famous init containers. But thanks to VPF, Cilium is doesn't need Sidecar. Why? Because all is directly with the kernel. Similar with Envoy, for example. With Cilium, we can go directly to the kernel and apply things. So it's other important point that we want to mention. The availability don't depend on about Sidecar itself. So I don't know, questions?
Thank you. We'll start with the
Yeah, question. No?
So I'll go around and use the microphone for you so
okay,
we can record the questions.
Hello. Is this on? So is this bypassing IP tables and kube proxy to do its networking stuff altogether? It's just going directly into the kernel, creates a VM there, and that's where you're getting all this telemetry information?
So nice question. Effectively, for the people that are working with firewalling generally, IP tables, EB tables, hex tables, all that kind of layers that are embedded already in the Linux network stack are running also inside the kernel. You know that mod probe IP tables and so on, it's necessary for performing all of those activities. eBPF is giving Cilium the ability to write a specific knative usage of that interface. So you are filtering the information thanks to eBPF from the kernel to the network stack. And that example that I was showing you about Google versus Microsoft is not just to say that one is better than other, but especially to say that we are able to create an additional layer that generally in IP tables would require resolving because it's only on the IP layer. It's not layer 7 or the OCI standard. So we don't know the application layer in IP tables, while here we know. It's not really a replacement. It's probably an additional resource that Kubernetes can count on thanks to the eBPF technology. Everyone familiar with eBPF should say also that you can use that outside of Kubernetes too. It's not a must. But for Kubernetes, the advantage is that you can really replace and be more specific on what is firewalling. If you have been using a platform like WAF of AWS, Web Application Firewall, it's very similar to the concept that you can add a sort of proxying, not specific proxying, but I was not showing you a rule that you can add to the HTTP layer that is, in example, on routing. So /index.html possible, /about HTML not possible for that pod that is running in Kubernetes filtered by annotations.
Yeah, this is Sumant here. My question is, in a service mesh world, sidecars are critical. With Cilium, how it is gonna impact the service mesh kind of use cases?
So service mesh, in this case, is something that Cilium is able to provide as a native resource with the ability of using resources like gateway and similar. In the case of specific Cilium network policies, you can effectively filter the resource, but it's not really what you can do with, an example, the Cilium API gateway. The API gateway is able to give you the ability of using the service mesh also for canary deployments. We haven't covered that here because it was expressively focused on the network security. But obviously, on service mesh, the observability that is running on Grafana would have been tracking also the service mesh ability that you have when you create a specific Cilium service mesh. It's another custom resource definition of the Cilium bundle API extension. So if you go to Kubernetes and you start looking at how many resources in the CRDs for Cilium are added by the operator, that is basically having a lot of controllers on each of those resources, doing a reconcile logic. When you add a service mesh resource in the CRDs of Cilium, then it will immediately trigger all the things that are related to observability, but not necessarily to network policy if you don't specify something that is labeled or annotated that way. So they are independent, but coming from the same stack. There is another thing that we could add. Cilium is also a replacement for Istio multi-clustering. We are not covering that here, but in your case, the service mesh and the multi-clustering are also isolated from that kind of policies that you can have, And you can just rely on network like it was for IP tables or for a squid proxy that was filtering a specific route. What we cannot do with a specific HTTP route is the URI yet. We can filter the whole URL and the route, but not the URI. So what is coming after that with query parameters, we cannot.
Hi. One Kubernetes flavor is CoreOS OKD. Will Cilium run on there on CoreOS?
So on CoreOS, I don't know who of you is using and knowing CoreOS before of Fedora. CoreOS was initially a very good operating system that was running containers, initially with Rocket Engine. Then it was acquired by Red Hat and Fedora and maintained. Initially, it was using a security stack that was called Tecton, and it was a very good alternative for running Apache Mesos. If you run Kubernetes on top of CoreOS, it's like running Kubernetes on top of Fedora Atomic. So you rely on a lot of features that are implemented on the network stack by Red Hat to run containers, and it's quite hard. In my case, I've not been trying in the last time, but I've been using CoreOS a lot in the last 10 years for Mesos specifically, not for Kubernetes. The Rocket-based kernel and the fact that they adapted to Docker, the fact that they are using Podman and Cryo as a container engine should be disposable with Kubernetes, but for Cilium, it can be tricky to have it up and running, and there is something that we were discussing previously with Gerardo about Cilium's network stack. It's easy to run it on top of an existing RKE2 cluster, Kubernetes, but when you go to EKS, AKS, and Koreos, you could face specific problem related to the installation that are exactly for the kernel differences in drivers, and probably it will be not yet the time for that to run the Cilium on top of Koreos as a Fedora Koreos distribution. If you do that, probably you will find some challenges to face.
I'm wondering when you guys start supporting URIs.
Can you shout more?
Do I have to press a button? All right. Can you hear me?
Yes.
All right. When you move to like implement URI support, do you plan to expose that in Hubble, and will we also be able to see headers and things like that? Or is it just going to be like the path like it seems to be today?
So in our case, I will give you a real fast background to see how we went to the adoption of Cilium. Our background was Calico and Istio with Envoy proxy, so everything related to sidecar containers. At that point, you know that Envoy proxy is using that ability to filter URI, also, for example, in Canary deployment for service mesh that are working with 99.1 deployment or blue-green deployment. But sincerely, we are not yet using that feature. I can say that Cilium is able to provide you the layer to implement the URI filtering when you are using the service mesh, not the network policies. So if you use the Cilium service mesh, you can effectively work with Canary. You have two versions up and running on the same namespace with a percentage that is establishing which one of the service is responding more than other. You don't have an instrumentation yet to track there. You should install Kiali or Jagger like you do in Istio. At that point, you are able to see the URI filtering. The big advantage using Cilium is that you see almost the same, but you don't install Istio, which is very painful. And second point is that it's straightforward. So it's something that really you can run a Helm install for that kind of resources, and it will be transparent.
Any other questions?
Go ahead. You want to answer some questions?
This was mostly around the performance between the alternatives. So if you're running Istio versus running Cilium, is there a lower footprint and lower overhead with Cilium than there would be with Istio, besides the sidecars?
So basically, comparing performances between Istio and Cilium. Here we can say really easily that you can try that on kind, and you will see that Istio is overwhelming the system. It's creating a lot of resources. When I used the command line, I was not really looking at the screen because some comments was there, then I was using auto-completion. It was really easy to work. When you use Istio, probably I would have been switching constantly the terminal here to look at what I was effectively writing. And the fact that, first of all, it's using Envoy. So it's good because it's C, but it's evil because it's a sidecar container. So you lose the control of the stack. It's not an init container. In terms of advantages, the only thing that I feel it's still something they have to fix or find a solution is that in Istio, when you use canary deployment, you use SCaLE and Jagger. Here, they are not ready to go. For multi-clustering, Istio is very complex and will require something that will need to implement a sort of additional layer like a VPN. If you have tried to do multi-clustering, is someone here familiar with Kubernetes multi-clustering? It's a challenge. I don't know if you tried, but imagine that you have to connect two different clusters and you have two challenges. One is the one that we are facing in our current reality, that is pairing a cluster to another for a distributed system. So not for a cooperational cluster like Istio, having a pod here, another here that is running in China, one in the US, and they are doing the same activity but balanced. That is Istio multi-clustering. In Cilium, what I can do is to have a peer running here in China, another peer running here in the US. They are peering, not cooperational activity, master-slave clustering, but they are really distributed. So in our use case, in example, or what I work more in daily activities, I can do blockchain thanks to Cilium inside Kubernetes. That is still a big challenge, but it's not possible with Istio. So keeping on your answer back, Istio, they have to work better on removing the Envoy support, doing something more lightweight, and then we have to say in any case that Istio is paired to Calico and Tigera since a lot of time, so you will depend on the Calico stack for block affinity of the nodes, and it will add more complexity. Calico is doing the same. Let's say the true. It's not doing something different. But the point is that you have to edit the YAML files for doing things correctly, while here it's very straightforward. And there are no tons of custom resource definitions to call, but it's just something that you go and do. It's easier. So for me, if you have Istio, start to do the isovalent courses that are available for free, and you will immediately realize in one day that it's very simple.
Any other questions?
So probably before finishing, one thing that I want to add is our idea is don't say Istio doesn't work. No, Istio is a good project, but depends your needs. Depends what do you need in your company, in your job. I want to remember Cilium recently was graduated, Istio has way. So compare, enjoy it. The reason that we are using kind is because you can destroy your local cluster and no problem. So I hope that you enjoyed the presentation.
Destroy the cluster.
Yeah, destroy. And so for us, it's a big pleasure if you can come back to the presentation. So it is, okay, destroy the cluster. Yeah, with kind is magic. You can delete the cluster and have all the cluster itself. So again, it's a pleasure. Thank you so much. It is on links. Thank you.
This working? Nope. Wonderful. Is there a mute on this? It does work when I hit it. It's just really sensitive. Hello. Yeah, that works.
I think we're going to get started. People will continue to trickle in. So we welcome Eamon Ryan. Eamon Ryan is a field principal engineer with Grafana Lab, and he brings a pretty impressive background from VMware and Pivotal days as well, something we'll talk about later. Originally from Ireland, has been in the US for 10 years, slightly up north in the Bay Area, in Oakland, and he'll be talking about scaling Grafana, right? Prometheus, sorry.
Hi, folks. Yeah, so this is a series of fortunate invents, open source tool of solutions for scaling Prometheus. This is Grafana's little mascot Grat here, helpfully with a logo from the con on his hat. As Faisal said, my name is Eamon Ryan. I'm a senior principal field engineer at Grafana Labs. I've been at Grafana for almost 4 years now, literally like 2 weeks away from 4 years. Which is an eternity in relation to the company length. But yeah, we get to work a lot of cool technology there. Big fans of Prometheus. Grafana actually employs over 40% of the Prometheus maintainers. So we're big fans of it. We build a lot of solutions around it and to work with it. And lots of them open source, of course, which is what I'm here to talk to you about today. So I have a little disclosure up front. Obviously, I work at Grafana Labs. One of the main solutions I'm going to talk about that helps you scale Prometheus is a project that's built and maintained by Grafana Labs. That might create concerns of obvious bias, which is why I'm not actually going to recommend a particular one at the end. I'm going to showcase a couple of like more main contenders that includes ours, but I'm not going to tell you to use a specific one. I'm going to tell you about a few things about the different ones to help you make a choice there, but I'm not going to say one is objectively better because they're not. And if I said our one was the best one, you'd say I was biased. If I said somebody else's one was the best one, you'd think I was not planning to have a job for very long, probably. So I'm going to try to keep it unbiased. I'm just going to talk about objectively true things, and then you can take that information and kind of make your own decision from there. So, in case you walked into a talk about scaling Prometheus and you haven't actually touched Prometheus before, just a quick refresher. First of all, who uses Prometheus in the room? Everybody. Okay, almost everybody. Not everybody's hand was up. So Prometheus is an open source time series database solution. It implements a multi-dimensional data model. So all time series are identified by a metric name and a set of key value pairs, and then obviously a value for a metric. PromQL, which is the query language, lets you slice and dice the collected time series data so that you can generate ad hoc graphs, tables, and alerts, and all that good stuff that we need to keep things running. Prometheus has, whoops, it's too far. Prometheus has a few different modes for visualizing data. It has a built-in query browser UI, which is a bit more limited, but it does function if you were just trying to verify that a query is usable and does return. The most common way I see people talking to Prometheus is via Grafana, but that's not the only way you can do it, but Grafana does give you a lot more visualization options than you would otherwise have. And then, of course, you can address Prometheus directly via its own APIs and pull out whatever data you want in that manner as well. It's got pretty efficient storage, so it stores time series in memory and on the local disk in a really efficient custom format. You can scale it in using Prometheus Federation, which I'll talk about in a little bit, but it has limitations there. Each server that you run in Prometheus is independent, so from a reliability perspective, they only rely on each other and on their local storage. It's all written in Go, very easy to deploy. You can deploy it on Linux, you can deploy it in a container on Docker, you can deploy it in a Kubernetes cluster. Doesn't really matter, it works on all of them, although don't run it on NFS storage. It doesn't like that. It'll actually warn you if you try and start an NFS, and it will run, but it will tell you that your stuff will get corrupted, and it's not lying. It does do that. Let's see. Alerts are defined in Prometheus's PromQL language, and they maintain all the dimensions, and you can send alerts to Alert Manager and deal with notifications and silences and all that. It's got a ton of client libraries if you want to instrument metrics for Prometheus. 10 different languages, over 10 are supported, and you can add custom libraries and do your own custom instrumentation pretty easily. And there is a bunch of existing exporters and integrations that allow you to pull in third-party data into Prometheus. So if you have something that does not output data in a Prometheus format, and it's something that at least other people use, it's not something you built totally in-house, there's probably an exporter for that out there that will convert data into a Prometheus format that you could then ingest into Prometheus or something Prometheus compatible. So that's all the good stuff that a lot of you probably already know about Prometheus, but it has some limitations. And these limitations aren't necessarily deficiencies of the project, they're just non-goals of the project. So they're not things that the project was necessarily ever set out to solve, leaving those things to be solved by other solutions, which is why we're here today. So the first is around size. So Prometheus is a single process or single machine, which means you can only scale up, which means you can add CPU, you can add memory, you can add disk, but you can't scale out. You can't run a cluster of Prometheus servers. You can run a HA pair, but that's not a cluster. So you might be in a position where your metric needs are growing in your work, in your company, in your house. Maybe you have a really big house, a lot of stuff. And you keep adding CPU, you keep adding memory, and now this is like too big for a machine, or you're running it inside of a cloud provider like AWS, and you're doing bigger and bigger Amazon instances. And maybe you go all the way up to something like this, the R7A.Metal 48XL with 192 CPUs. And over 1.5 terabytes of RAM, and that's still not enough. And maybe it's still gone on fire and exploding and falling over. I have seen this. I have spoken to a customer who did this and literally was at the largest AWS instance you could get with like some number of millions of series inside it, and it was still falling over. And then they came to talk to us about it. So people do this, but eventually you run out of headroom. There's only so far you can go. So if you then run up to the top of what you can fit in one machine, what do you end up doing? You end up having more than one. So you have a second server, and maybe you send half your metrics to server B and half your metrics to server A, and that works okay. But maybe that results in a scenario where now you have 2, or maybe you have 4, maybe you have 6, maybe you have 8, and you connect all 8 of those up to one Grafana instance, and now what happens when you're trying to find metrics from those servers? Which data source in Grafana are you going to query? So you're going to be looking at Grafana going, oh, which one do I pick? Oh no, please help. And makes for a sad experience. This is also something I see pretty commonly. So people add loads and loads of these servers, and then they either have to have the overhead of figuring out which one to query, or they end up running some kind of proxy in front of it. So you can run, there's a project out there called, I don't know how to say it, PromXY, like prom proxy. But the problem with that is if any of them are slow, then your response is always slow. So it becomes hard to identify where there's an issue, if there is an issue, because you're trying to query like n servers at once. So also not really a great kind of setup, and one that people commonly run into. The third limitation here is around retention. So if you've used open source Prometheus, you know that the retention is going to be a week, 2 weeks, 3 weeks, mostly. You can set it longer, but it doesn't really handle that very well. It's not designed to. And so if you wanted to run a query inside of, say, Grafana that went back more than a week, you'll end up with, a graph like this, where you only have as far back as your retention actually is, and you're standing here looking around for, the rest of the data inside your graph, and it's just not there. This took an unreasonably long amount of time to get that GIF in there properly. The next part is around tenancy. So you have your Prometheus server here at the bottom. You might have, team 1 up here, team 2, team 3, team 4, team 5 at your company, and they're all getting metrics sent into the same Prometheus server, but there's no segregation in there, and there's no limits. It's either on or it's off. Aside from like rules you can make around filtering of metrics, but that's not really a tenancy. It's not really a team limiting thing. So you're effectively operating like you have just open floodgates all of the time, just pouring all these metrics into the one server, which means you can easily run into situations of like noisy neighbor teams. So one team just blows up the amount of metrics being sent into the system, and now everyone else has to suffer because of that, and they knock the whole thing over. And the next limitation here is around HA and resiliency. I briefly mentioned having a cluster before, so you might have 2 Prometheus servers that you run as a HA pair. But, as I mentioned, like one of the early slides, they run totally independently of each other. So they don't know they're in a cluster. They're basically there with a brick wall between them, and they have their own sets of config, their own sets of scrape targets, even if they're the same scrape targets, but they are maintained independently. They have separate disks, separate TSDBs, and I say no backfill here. There is methods of backfilling data into Prometheus, but a HA pair does not sync itself. Like there's no automatic syncing of data. So if you take one down to upgrade it, it's missing data while it was down, comes back up, it doesn't get filled in by the other one. So that's something you have to manage yourself. It's a totally separate activity. So what do you do? What are you supposed to do to like solve this problem? So there, if you go to Prometheus.io, there is a page of integrated remote storage solutions for Prometheus. It looks like this. There's a lot of them, and they're not all good candidates, and they're not all up-to-date candidates either. So this could be really misleading if you just looked at it at a glance. As kind of a zeroth round elimination, ones that I'm not focusing on here out of this list are, first of all, things that are not open source, because we're at an open source conference. Things that are SaaS only, because that usually goes hand in hand with not open source. So you can't run it yourself. And so that precludes things like TimeStream, Azure Data Explorer, BigQuery, Splunk, Wavefront, all these kinds of things. So I'm not really going to focus on any of them. There are some items in here that I'm going to mention, because otherwise somebody at the end is going to go, but what about X? And I'm just going to head that off up front. So here's the first round eliminations. The other one was the zeroth round, but here's the first round. So CrateDB is a SQL performant database. It has a Prometheus adapter, which means it's able to accept data in Prometheus format, and it's able to translate a query in PromQL into the SQL format it needs to return the data. So on paper, it should work fine. From what I could glean from it, I haven't used this. There's one maintainer. It's running on a 0.5.1 release version, which doesn't mean it doesn't work. Just means it hasn't existed for terribly, terribly long. I have never spoken to somebody who was using this, and so I didn't go into like further evaluation with it, because there's just not many references to people actually using this for something. So maybe a future one, which is why I have that up there, but it's not part of the larger analysis I have here. Next one here is Elastic. You can actually write PromQL or Prometheus format metrics into Elastic, but you can't get them back out in Prometheus format. So they'll go in Prometheus format, but then you have to query it in Elastic's query language, which doesn't feel like a solution for scaling Prometheus. That's a solution for moving stuff out of Prometheus, essentially. Elastic, as people probably already know, in observability world, changed their license to one that isn't OSI approved. So it doesn't really feel in the spirit of open source to have that in that list as well. Noki, or Nochi, this one lets you write data in, but doesn't let you read it out, kind of like Elastic. So that's not ideal. There is a Grafana plugin for Nochi, but it's really, really old. It hasn't been updated in forever, so I wouldn't say it even works still. Do you know you could write Prometheus metrics into Graphite? I wouldn't recommend it, but you can. So you can write it in, but again, you can't read it out as Prometheus. I don't know anybody moving on to Graphite. I only know people moving away from Graphite. So I don't think that's a good direction to go in anyway, but you could. grep TimeDB was an interesting one. I had never heard of it before I started writing this talk, but they are working towards a full PromQL compatibility. They're at 82.12% now. So it looks pretty promising, but by their own admission, like they're not like ready for like production prime time yet until they reach that point. But it does look like a cool project. So maybe the next time I do a version of this talk, that'll be further inside the deck. You can write PromQL, or not PromQL, Prometheus metrics into InfluxDB, and you can query them back out. There is plugins there, but Influx decided that clustering in HA was no longer going to be in their OSS version, so that kind of precludes it from being a valid option for scaling Prometheus, I thought. M3DB, I think previously used to be a really good candidate for this. This is the one that was originally created at Uber, but they haven't had a release since April 2022. And that's unfortunate, but obviously you don't want to use something that hasn't been updated in 2 years. So I don't really think that's a good choice. Similar for OpenTSDB, hasn't had a release since 2021. Probably not a great option either. Doesn't look like people are still developing it. And PromScale, definitely not still being developed. That one actually has an announcement that says this is done now, whereas the previous two don't. They just don't have any more things going into them. But PromScale said, we're done, sorry, goodbye. So that's all the first round ones. So before I get into like the main four I ended up evaluating, I want to talk about Prometheus Federation. Is anybody here using Federation? Nobody. Good. I'll talk about it a little bit and why it's not really the best solution for scaling. It has its uses, but for just scaling to a larger setup, it's only useful if you have a very specific setup in mind. So you might have, we'll say, a bunch of Prometheus servers, and you could have a top level of Prometheus that's then going to reach out to these servers on their federate endpoint, and it's able to choose which series it wants to pull in from the others into itself. That's great in a scenario where the top level one is meant to hold things like global aggregates, and then the other servers are meant to hold the more localized granular data. That's exactly what it's for. But if you were trying to go for a scenario like, oh, I just want to pull everything up into the top level one from all my like leaf Promethei's, which is the correct plural, by the way, from all my leaf Promethei's, then what's going to happen? It's still just a single process, so it's going to reach out to all these, pull in every series from all these Promethei's, and then it's still just one machine. So you end up in the please help scenario again. It'll just fall over. It's not some super magical thing. It's still data going into a system, and that system only scales vertically, so there is a runway that is only so long there. So the Federation is like a lot of management and overhead at best. If you only have a small setup, it's okay, but can you imagine trying to figure this out for like 20 plus Prometheus servers, and which things are being rolled up and which things are not, and now this becomes this like overhead nightmare. So that's why I don't really consider it a good contender here either. So the actual contenders I ended up with, there's four. So we got Cortex, Victoria Metrics, Thanos, and Grafana Mimir. As I said in the beginning, I'm trying to do this in a really unbiased way. I'm not even going to recommend a particular one, as I said. They're all very valid choices. I'm going to let you know their factual status on several criteria that I think are important when you're considering a production rollout of one of these, and then you make your own decision. All the information that I pulled out is coming from the public docs of each solution, or something I found in the relevant GitHub of the project, which means if I'm wrong, it was wrong up there. So there's no opinions here. This is literally what I could just find online. So don't come attack me if you're really attached to one of these products. But if I'm wrong, do come tell me, and I'll tell you. I actually, in my speaker notes, have the link for where I found every bit of info. So I will link it to you, and you can go fix it. One other thing, so performance, which you might think is the most important thing here, isn't enough. There's a very recent article on motherduck.com called Performance is Not Enough. And there were 2 lines in it that I thought were really, really pertinent in this scenario. So one is that performance in general, and general purpose benchmarking in particular, is a poor way to choose a database. And I think that's so accurate because a lot of databases end up commoditizing further and further the longer that they exist. There isn't some secret arcane art that some programmers know and some don't, where they're going to make something 100 times more efficient than everybody else and nobody else can do it. If somebody finds out a novel new technique or a novel way of accomplishing a particular task that's way more efficient, its competitors are going to do that eventually too, because that's just the natural way that stuff works. Somebody figures something out, people emulate it in their product, so the performance ends up converging over time. So solution A might be 30% faster in their newest release because they figured something out. But then B, C, and D will all move towards that level of speed in the next few releases anyway. That tends to be how it goes. So choosing a solution purely on who's performing fastest right now isn't necessarily going to help you when whatever choice you make, you're probably going to keep it for at least a few years, and all the other ones are going to be at the same level anyway, or at least something close to it. So don't make performance your only criteria. The second line here is you're better off making decisions based on the ease of use, ecosystem, velocity of updates, and how well it integrates with your workflow. So can you use it in conjunction with your other tools? Is it still being actively updated and stuff actually gets fixed? Is it being updated to run on the latest versions of whatever dependencies it uses for security purposes as well? Is there a good ecosystem of plugins around it? Is it portable? Does it introduce any kind of technical debt or lock-in? Like all these things I think can be more important than the performance, as long as the performance is at least some kind of baseline of okay. And this came from Jordan Tigani at MotherDuck, who, yeah, I thought that was a great excerpt. So I came across this like days before I wrote this and said, cool, I'm going to borrow that. So these are the criteria I'm going to go through for each of the 4. And I'll explain why for each one. First is the operational mode. So this is whether it's centralized or using some other kind of model. This is just so you know how to actually deploy it and how it works, like pull, push, all that kind of stuff. The second is how the long-term data is being stored. So is it being stored on disk, or is it being stored in object storage, or is it being stored in SD cards, or how is it actually being stored long-term? This has implications for reliability, it has implications for cost, and so those are worth considering because you're going to be paying for this infrastructure anyway. The third is, does it support OpenTelemetry native ingestion? So there are solutions for converting Prometheus metrics into OTel format, but maybe you're pulling in metrics in OTel native format anyway, and you'd like to keep it in OTel native format, which is a totally valid ask. And so you want to know, do any of these backends support it, or only partially support it, or what's happening there? Good for future proofing. The next is around PromQL compatibility. So some of the solutions, including the commercial SaaS-based ones, will tell you that they accept Prometheus metrics and let you query in Prometheus query language. But they don't actually have full compatibility of PromQL, which means you can't run all the same queries. They just don't work. And anytime you have to deviate from a full PromQL compatibility, that means you accrue technical debt because you're going to change your queries to match this other syntax that's needed for it to work. And it means if you ever move off of that solution, you have to change them back. So this is can be a very dangerous spot to end up in if they're not fully compatible. Next is the known SCaLE. So I said performance is not enough. SCaLE isn't everything. You might know what SCaLE you need as a maximum, and maybe all these are larger than you would ever need, in which case it doesn't matter. But maybe it does. So I tried to pull some kind of known online reference that says how far these can scale, at least in write. By write, I mean like write load. Querying is much trickier because while you can say, oh, we can ingest 15 million series into our solution, it's we don't really necessarily have a standardized benchmark for the read path. Like we can publish benchmarks that say we did these kind of reads, but then the other solution says we did those kind of reads, and the data can be different, and the queries are different, and so it's hard to measure those directly. So I don't have that one as one of these, but it could be something to consider as well. The next is multi-tenancy. So I said in one of the limitations why that's a problem, or why it might matter to you. I have spoken to plenty of people for whom it doesn't matter. They just want to dump everything in one tenant and they don't care. But if it does matter to you, I have that here. The next is, can you utilize limits on a per tenant basis? Because you want to prevent team A from influencing team B. I got a couple more. Native histogram support. Native histograms are the updated Prometheus histograms. These are the ones with also called exponential histograms. I think there's another name, but it escapes me now. Native histograms is the official name. This is histograms that can have as many buckets as you want and only correspond to a single time series. That feature is actually still experimental in OSS Prometheus. So that means that any solution that has it implemented, it still officially can only be experimental because the underlying feature is experimental. But some of them have it and some of them don't. Downsampling, this is when you want to reduce the resolution of the data over time. That's important to some people for different reasons. To some people it's important for querying. It's easier to query less data points if you're trying to query over like years. And for some people it's for cost. If we reduce the resolution of the data, we reduce how many data points we're storing, and so it's cheaper. Or that's the thinking anyway. And the final one I have here is how many releases have they done in the past 2 years? And I did it on minor releases. I didn't count patch releases. Minor releases only. Not saying everybody does Semver correctly. But I counted it on minor releases. It's also not the most accurate metric though, because some people put a lot into a minor release and some people don't. And some people put in breaking changes into minor releases and some people don't. So it's kind of not the best gauge, but it's an indicator, so I included it. So let me jump into them. So we'll start with Cortex, not for any particular reason. The mode that this works in is a centralized cluster. So it actually switches the Prometheus model around from scraping to a push model. So that means you have to send data into it via the remote write protocol, which Prometheus supports. You can send that from not just Prometheus, but anything that can support that protocol. You can write your own curl script that does this if you want. But the main things people do this with are regular Prometheus servers. They can be configured to do that. They do that with the Prometheus agent. They do that with the Grafana agent. You can configure the OTel collector to write in remote write format. There's an exporter for that. You can do this with Telegraph. You can do it with tons of things. So as long as it's in that format, this solution can accept it. I think they all can actually, but this one accepts it in that way, but it becomes a central cluster. You push the data out to it instead of it reaching in and scraping out. So it inverts the model. The second here is that the most recent data in Cortex is stored in block storage, so it means it's on disks. And then the long-term data is stored in object storage, which makes it really cheap to store. And so the long-term data is just pulled in from there. There's fancy indexing going on and all that kind of stuff. There's not usually a huge concern with that, but if you are deploying, say, like on-premise in your own data center and you don't have object storage available, well, this will probably be a problem for you. So you should look into getting that. The next is OTLP ingestion. So for this one, it's a work in progress. I was able to find an issue that indicated they are working on it, but it's not there today. PromQL, 100%. Perfect. So nothing to worry about there. I will say the PromQL indicator I have here, there is a third-party company called PromLabs, and the last time they ran a big battery of these was a couple of years ago, but they tested a ton of backends with the same exact compatibility test, and that's how we get these results. So they basically said all these ones are 100%, these ones are not, and so on, and so I'm pulling from there. They're able to submit, the vendors can submit their own result to that site and have them published, so I'm just going off of the latest one that's up there. Known scale for this one, I couldn't find a definite number. I found it to go up to millions of series, which was fine, but I didn't get a specific number. They had there was a Medium post from, sorry, no, was this the Medium one? No, they had a case study published from a company called Gojek, and they had listed millions, but not how many. So that's all I had to go on. The multi-tenancy, it is there. They do it via headers. So you use the Xscope org ID header. There isn't necessarily auth around any of these for any of these solutions by default. You can add your own auth layer. Like you can put a proxy in front and have it authenticate and then have that attach the header. You can do that and that works, but this doesn't have any auth by default. But the tenants are separated by this header data. So if you just write metrics with this header set, it just goes into that tenant. If a tenant doesn't exist, it will exist once you write something to it, just automatically. It does have per tenant limits. You can set all sorts of limits like how many series can be ingested in each tenant. You can say how many labels can be on every metric, a maximum. You can say how big they can be in various different types of sizes. You can set an ingestion rate. You can set all sorts of things. Native histogram, not supported in Cortex yet, but does seem to be under active development. It looked pretty far along, so that'll be there soon. They're also working on downsampling. I think it wasn't as far along, but it is something that's also currently being worked on in that project. And I found that they have about 2 minor releases per year over the last 2 years. So, pretty good. Next one here is Victoria Metrics. Bit different in a few different ways. In the mode, it's the same as the previous one. So central cluster, remote write, accepts all the same things, works fine. Storage mode here is different. There's no object storage used in Victoria Metrics. Everything is done on disks. And this can mean, like, this can be viewed as a good thing or a bad thing. You could say it's a good thing because there's no dependency on object storage. That's one less thing you have to deploy. Some people might say it could be a negative thing because object storage has a much higher reliability score than disks do. Disks fail more often than object storage does. So it depends on how important that is to you. Regular disks can be more expensive than object storage. Object storage is historically quite cheap, but of course that depends on how you use it. So good thing to consider. They have OTLP ingestion already released, so that's great. The PromQL compatibility is 74.16%. On that last PromLabs test. The way that this differs from the Noki one that I mentioned in the prior eliminations is that while Noki is working towards 100% compatibility, this appears to be a deliberate decision, which is kind of a more unique take. So if you follow the GitHub issues, you'll find that what seemed to happen was the authors of Victoria Metrics didn't like the way PromQL did some things, and so they essentially have like a partial fork of the language called MetricsQL, where they did the things differently that they thought were better, which is fine. That's a fair take. But it does mean that if you move to it, you have to change some query stuff, and if you move off of it, you have to change it back. So if you like how they do it, sure, go for it. Known SCaLE, I did find an article on Medium from Criteo, I don't know how to say it, engineering, where they said they got it up to 1 billion active series, which is really cool. So pretty big scale. Multi-tenancy is there, but they gate the multi-tenant rules in their enterprise edition. So you can send stuff to different tenants, but if you want alerting rules on a per tenant basis or recording rules, you have to pay, which I thought was an interesting choice. Per tenant limits, same thing. They only exist in the enterprise edition as well as getting statistics on a per tenant basis. Native histograms are not there. I couldn't find anything that indicated they were planning to add them. There was a GitHub issue where they were suggesting people to use their histogram version, like it was called like Victoria histograms or something like that, but they couldn't find any indicator that they were working on this. Downsampling is there, but it's in the enterprise edition. But their velocity is really high. So I found between 5 and 10 miners per year. So very active project, which is pretty cool to see. On to the third one. Thanos, this is probably the most well-known one that I'm aware of. I don't think like anybody who talks about scaling Prometheus always knows of Thanos, so it definitely has the most name recognition. This one has 2 modes. So it can run as a sidecar attached to Prometheus processes where it queries those Prometheus directly and sends it up to the cluster. That means that recent queries are actually live queried from these Leaf Prometheus servers. But you can also send data directly into it in a centralized model via the Thanos receiver mode. And you can run both modes at the same time, depending on your use case, and maybe you have limitations around network traffic directions and firewalls and all that stuff. So kind of versatile from that perspective. Storage is similar to 3 out of the 4, so block storage for recent data, object storage for other data, which is fine. It actually there's a lot of code shared actually between Thanos and Cortex and Mimir around how data is stored in object storage. So that's kind of cool to see, very, very open sourcey. OTLP ingestion doesn't seem to be being worked on right now. I found an issue where somebody said, I would like to work on this, and nothing else. So I don't know where it stands. It's certainly not anywhere I could easily find. PromQL, 100%, perfect. I found for SCaLE, they have a case study published on their own, on the Thanos site from a company called Medallia, where they say they got it up to 1 billion series in this with a crazy architectural diagram, but they said it got up to 1 billion. I'm not here to validate the numbers. I'm just telling you this is what I could find. So that's cool. We've run stuff up to 1 billion, and like you can do it, but like it's work. Multi-tenancy, they have it in Thanos, but it's done slightly differently. It's just using external labels. So it's a little looser. You are storing everything in like a big TSDB instead of separate ones per tenant. But it still can function, but it does depend on how you do your, like who has the control over your metrics infrastructure. Is that all controlled by a central observability team, or is it controlled by individual teams? Because if it's individual teams and it's only done via labels, then there is room for them to do things that they shouldn't really be able to do. But totally depends on what you need for your environment. Per tenant limits, they have them as experimental, but only for the receiver mode because of the nature of it. So receiver mode is receiving stuff via push from remote write, so they can push back. But if you're doing a sidecar mode, well, now you're scraping, and that's a different entire setup to have to put limits around. So it's a bit trickier to do that in. Native histograms, they're in there, already done. Downsampling, in there, already done. So you can just take that and do that straight away. And the velocity is about 3 to 4 miners per year over the last 2 years. So pretty good velocity as well. And on to the last one. So this is Grafana Mimir. The mode is similar to most of them. So it's a centralized cluster. You remote write up to it. Prometheus agent, Grafana agent, Telegraph, whatever, doesn't matter. The storage, block storage for recent, object storage for the older data, nice and cheap. OTLP ingestion, already there. PromQL, 100%. Known scale, 1 billion series. We have a blog up on our site about running it up to 1 billion. There's at least a couple customers running it who have run it up to 1 billion. I don't know if they do it all the time, but they have done it. Multi-tenancy, this is the same as for Cortex. If you're not familiar, Mimir was actually a fork of Cortex, so it inherits a lot of things from that. But this happened in 2022. So in 2022, they were the same, and they've diverged since then. But the tenancy system existed prior to that, so it's the exact same system. As a result of that, same system for per tenant limits. We might have different limits now, or added more, but it works the same way. Native histograms are already in. Don't have downsampling today, but it is something that we do plan to add. The way that, like, we actually put off working on downsampling for some time because most people who wanted it, that we spoke to, wanted it for cost-saving reasons. But with the way that Mimir works and its use of object storage, the storage cost is actually less than 10% of the TCO. So it's not the area to spend a lot of time optimizing because the cost saving isn't going to be that high. Now the other use case, which is if I downsample the data, it will make long-term queries easier because there's less data to iterate over. That's more valid. That's why we are going to add it anyway, but definitely pushed it out because it wasn't going to help with TCO very much. And the velocity is about 4 or 5 minor releases per year over the last 2 years. We're 2.12, I think, is about to come out. I saw a release candidate up there already. So, yeah. Here's the big table, which was fun to try and fit all this on the same page. I knew I'd see a few phones go up for that. Yeah, so this is the big table. This obviously is a point in time. This is how they are today or this week. This will obviously change over time. Some of these features could move from enterprise into OSS, or some of these numbers could change, or architectures change, anything like that. But as of this week, this is all true from what I could find online. Again, if I'm wrong, it's wrong online. Don't blame me. So there's lots of good options here. There is no single best answer, really. It really depends on what's right for your needs and what's important to you in your environment. There are things that you might care about that we don't care about, things that we do care about that you don't care about. And the big thing is we're all just trying to use Prometheus and scale Prometheus because we like Prometheus and just want to keep using it and stay in that ecosystem and just, keep everything working well and our monitoring functioning properly. All of these solutions work with Grafana, which is great. Love hooking up everything to Grafana as much as we can, and this keeps our little mascot here very happy to see it in use. So that brings me to the end. I can do some Q&A. Just wanted to highlight in the top left, my colleague Ananya is doing a talk on incident response with OpenTelemetry at 6:15 today in room 107. We do have a booth in the hall. If you haven't been in the hall, come to the booth. I'll probably go there for a bit until Ananya's talk. So after I leave here, if you want to come ask me stuff, you can. And yeah, if you want to check out some of our other open source stuff, it's on there. We've got something for logs, for traces. Metrics is what I talked about today, but we have logs and traces as well. So I can talk about any of those with you. So other than that, I'll do questions.
All right, I'll come up to you so we can record the questions as well.
Is this working? Okay, go. First of all, is this slide deck available anywhere for us?
Not right this minute, but
Okay.
I probably could, yeah.
Okay, I was just curious. And then the second question, no, I forgot. Never mind. Oh well.
Thank you.
So first of all, great talk. Loved getting the overview of the whole ecosystem. Why do you think so many of the solutions you presented only use remote write sort of as their ingestion method, whereas Thanos has the sidecar alongside remote write?
So that wasn't like super loud because that mic is kind of weird, but
Oh.
it's okay. The question was, why do I think so many of the solutions use remote write as the ingested method, and Thanos is the only one using the sidecar method? Which is a great question. I know why that is for Cortex and Mimir. So the reason for that is Thanos existed before them. Cortex was created in part to deliberately have a slightly different model to what Thanos did, because we like Thanos, but we thought there were things about it that didn't work as well. So that model that Thanos has does function, but the fact that it then creates this reliance on all these leashed Prometheus servers means that if you have an issue with those, you actually don't have a full picture of your data. So if there's an issue out in this network where this Prometheus is, and you want to query data that was coming from over there, it's not going to be present. Whereas if everything is pushed up to a central cluster, you always have access to all the data that's in there. It does mean that you can also have your query time affected by one of these being slow, of these outer like Prometheus servers. And so when Cortex was being created, we wanted to not do that. And so we did it the other way. Excuse me. So it was a deliberate choice for that. I can't speak to Victoria Metrics. I don't know why they did it that way.
Thanks for putting this together. I have two questions. The first question is: do all four of like the contending solutions all use Prometheus adapter?
Because they all use Prometheus what, sorry?
Prometheus adapter.
Prometheus adapter. No, I think Prometheus adapter, when I looked, it was only intended for, it was like OpenTSTB and Graphite, and I think like one other one. That's what's listed on Prometheus IO for the Prometheus adapter. But do you mean like just for writing metrics into them? Or like, or you mean like how they're translating everything?
So there's like the custom metric scaling. If you want to scale off of like Prometheus, right? In Kubernetes specifically, is it compatible with like Mimir or like Thanos?
Oh, so can you use the sorry, I was thinking of the Prometheus adapter, which is different to the metrics adapter. Totally different thing.
Okay.
So like the question is like, can I use the metrics adapter so I can use the like pod autoscaler within Kubernetes? You definitely can for Mimir and Cortex, because I was working with Mimir before when it was still Cortex, and they both supported it. I don't know for Victoria Metrics because I haven't tried, but it should just be passing through queries like normal. So as long as your queries were valid, I think it should still work. I don't know how it handles the PromQL but not quite PromQL part. That part could be a little different, or maybe it just passes them through normally and it works fine. But the other three definitely do work.
Okay. And then the second question was, I noticed that the Grafana agent and the OpenTelemetry collector are really similar, but they're not quite the same. And I think there was like a fork at some point. What was like is there going to be like compatibility between the both of them like throughout?
So compatibility between the Grafana agent and the OTel collector?
Yeah. So could we just use OTel collector instead of the Grafana agent?
So the answer is you can. The short answer is you can do whatever thing you want. There's lots of ways to do it. What happened was we originally created the Grafana agent as something more lighter weight than a full Prometheus server when you want to remote write metrics out. Because for many people, if they're going to remote write metrics out, they're not actually going to query that Prometheus server by itself. So that Prometheus server having its own TSDB and query engine is redundant and a waste of resources. So the Grafana agent started out as Prometheus, but we ripped out the TSDB and the query engine and just kept the service discovery and the scraping and said, that's a Grafana agent right there. It's come on a lot since then, but that's what it was like in like 2020. In relation to, and as a side note, the Prometheus agent was actually created after the Grafana agent as a subset of the Grafana agent. So we went to the Prometheus project and said, hey, do you want like an agent? And they were like, we don't want all this extra fluff that you put in there, but we'll take like the core bit, and that's the Prometheus agent. So it actually came in reverse order from Grafana out to Prometheus. OTel collector is interesting because like it was a totally separate thing, but the Grafana agent actually includes now a ton of OTel collector components that you can optionally use. So you can use the Grafana agent and only use Prometheus-based components, or you can use the Grafana agent and use a ton of OTel components. And some of these are direct code copies over from the OTel collector project, so they work identically. Some of them aren't, because some of them are tweaked slightly to work better with like our solutions with less work on the user. And so it's kind of a mishmash of like whatever you think you'd want to do. There's an effort on our side to like, we're kind of shifting towards like the Grafana agent is basically our distribution of the OTel collector because it includes all these pieces. So you can use either. You can certainly write with the OTel collector directly to our stuff. You can use the Grafana agent. You can even do a mix. So I've seen people do a setup where they are collecting with the regular, what do you call it, vanilla OTel collector, close to their workloads. And then what they're doing is they're forwarding that into a Grafana agent, and then they're doing some modification of the data in there, some enriching of the data in there, and then they're sending it out to Mimir or to our cloud or to something like that. And so like you can kind of combo these things together in whatever Lego brick fashion you really want to, and everything works.
Yeah, do you see concern with the split between Cortex and Mimir? Do you see concerns with the future of Cortex, like development?
Concerns with the future of Cortex development. So that's a great question. If you were to go to the GitHub page for today, you'd see that the maintainer list is 4 people now. It used to be a lot larger when we were directly on it, but when we forked it, I don't directly code it, but all the Grafana people moved off of it after the fork happened. I think like 3 of the maintainers work at Amazon because I think it is the basis for Amazon managed Prometheus. And then one of them is at like Adobe, I could be wrong. There is an issue I found around like the CNCF was asking questions for them, and they said that they have like a lot of extra contributors, but they haven't added any new maintainers in a bit. So like, I don't think I'm in a position to make like a lofty statement there, but that like, I think that is a valid question. It definitely is still getting releases, which is why I included that they are doing 2 miners a year, so it's still moving. Looking back at the table though, it doesn't seem to have the same velocity, certainly. Like it's doing releases, but not as many. And I would say some of the major stuff they have in flight has been in flight for quite a while. So I'd say it's a slower moving project, but I wouldn't say it's like in massive trouble at the moment.
Any other questions? Okay, thank you, Eamon.
Thanks, folks.
Hello? Okay. Sounds good. Just a couple. Yeah, well, I came in today, so this morning caught 2 sessions. But yeah, the backstage talk was kind of interesting. We're working on something related at Spectro, so it's always good to find out what's happening in the, this whole IDP space is blowing up. Yeah. Yes, the developer tools stuff is interesting. Yeah, I don't know, had chatted with some people in the floor, guys from Flocks. What they're doing is kind of cool. I'm interested in the dev tools stuff, so it's a different approach. There was a whole DevOps track yesterday. Oh, was there? Oh, okay. Should have come here a day earlier, but yeah, some good stuff. Yeah, that's yeah, I don't know. We're trying to do too many things in my humble opinion, actually, but we have some ideas for that too. Our Edge AI offering doesn't really. Yeah, there's some interesting problems though, like distributed inferencing that Saad, our CTO, wants to start productizing. Not solving the fundamental problems. We don't have anyone in house with that expertise, especially not myself. But there's like productizing it is an interesting opportunity with our Edge stuff. But yeah, all this, it's wild. All the rate of change, it's just really something. Yeah. Yeah, there's a lot of a lot of that. Yeah, I mean, forget our tech industry. There's just whole other aspects of, I mean, I don't know, law, radiology. Like, I don't know. Should be very interesting. Okay, well, it's on, and I'm not getting any. Oh, no, I am. I think I just need to put it on my shirt. Hello? Hello? No, that's not. Test. use the, or how's that? Is that picking up? I don't think so. Hello? I'll use that.
I'll prove this one.
Hello. Yeah.
Maybe turn this off just so it doesn't fiddle around a bit. That's okay. We have a holder too if you want it
Oh, okay. Perfect.
aimed at your face.
Perfect.
Put a holder.
Yeah, that should do the trick. Thank you. Should we give it another few minutes, or?
You know, we're 1 minute after, so. Thanks for joining us. Tyler is visiting us from New Mexico, and I'll let him go on and introduce himself and his topic. Thanks, Tyler.
Sure, thanks, Steve. Hi, everyone. It's late on Saturday, so I appreciate you all being here. And I'm, thrilled to be here, and it's my first SCaLE. Honored to be presenting to you today. So, I have an intro slide I'll get to in a second, but today I'll be presenting self-healing clusters, game of nodes, and scaling the throne. It's kind of some horrible wordplay, but might resonate with some of you. Mostly talking about a couple different open source projects that we can dig into to understand how to make more resilient, stable Kubernetes environments. And just feel free to interrupt me at any point if you have questions. A little bit about me. I've been working hands-on with Kubernetes and Go since 2019. I'm in charge of SpectraCloud's advanced projects team, so I like getting hands-on with all the latest Kubernetes tech, building POCs, and also working on our backend. And when I'm not doing that, I try to get outside and play with rocks. That's me. Feel free to connect on LinkedIn. So today, I'll just go over some of the challenges that people face, what makes clusters unstable and common pitfalls, and then talk about the heroes of the story, these 3 open source projects, and then we'll have a demo, and maybe there will be a shameless plug at the end. We'll see. All right, so the challenges at hand. Basically, stability is key, and as everyone knows, with Kubernetes getting more and more traction, we are now seeing production-grade workloads that are running mission-critical software in a couple different categories. So AI, ML use cases are big. Video streaming, we have gaming platforms running in production, medical imaging, and when you have that kind of a situation, you really don't want any downtime. And also, we basically are seeing a proliferation of clusters, bigger clusters, more stuff going on as the ecosystem explodes. I don't know the last time you looked at the CNCF landscape poster, but there's just so much to choose from, and it leads to just increasing management complexity and growth pains. And with that being the case, how can we prevent service outages and degradations? And there's a few simple things we can do. So, a lot of the time you look in an environment and you realize that every single pod is receiving the best effort quality of service because people don't necessarily even know about quality of service. And that just relates to whether or not pods have specified resources and or limits. So there's 3 different quality of service classes, guaranteed, burstable, and best effort. But in a situation where everything's receiving best effort quality of service and you start encountering node pressure, then anything could get evicted. So if you want a stable environment, you probably should be delineating what needs a higher quality of service versus what might not be so mission critical. So that's just like one very brief example of something to be aware of. And I guess, I'll just dig into it a little bit more, which is that if you specify limits and requests for a pod and they equal one another, you'll receive what's called guaranteed. And then if you specify at least a memory request or a memory limit, that'll be considered burstable. And then best effort means you just didn't specify anything. And then when there's node pressure and things start getting evicted by the kubelet, you will
be evicted sooner if you're in the best effort category, and there's lots of things that get taken into consideration, but that's just one of them. Okay, so what else makes a cluster unstable? Really, when you start thinking about stability, you have to understand pod eviction and pod preemption, and who's doing that when. So when node resources get low, aka node pressure, the kubelet will start evicting pods. And when it does that, it takes into consideration things like priority, quality of service, and many other things. Pod preemption, on the other hand, is where if you have nodes that have filled up and the scheduler is trying to place additional workload, it needs to make decisions about how it's going to do that. It may evict running workloads that have already been online because there's a new workload that needs to be scheduled and it might have a higher priority. So priority gets taken into consideration with preemption as well. And there's a bunch of different stuff in the cluster that you can configure to impact the types of decisions that get made by the kubelet and the scheduler when you're running into a resource crunch. So some of that I've already touched on, but understanding priority and priority classes is a good place to start. By default, everything's going to receive the same priority, but you can assign a priority class name to any pod and then associate that to there's a integer valued priority that is associated with the class, and you're in a ideal world segregating your workload based on how important it is to you and defining a higher priority to workload that you don't want to be preempted. And then resource quotas, they're double-edged sword, so they're important because you might be in you might be operating multi-tenant Kubernetes clusters. A common pattern is like to have a team per namespace, or you might be running third-party workloads, truly multi-tenant cluster. And in that case, you want to prevent noisy neighbors. You want to ensure that namespaces are receiving a specific amount of capacity, and you do that with a resource quota. So you can define the total number of objects, like config maps, services, secrets, that can be provisioned in a namespace. Also, you can dictate the total CPU requests, memory requests, storage, etc. But in order for resource quotas to be implemented, you need every pod to define requests. And if it doesn't, it won't get scheduled. So this is another common pitfall, is like an application developer's trying to apply a resource into a cluster, and an administrator has applied a resource quota into the namespace that they're trying to schedule their pod into, and it's not getting scheduled, and they don't know why. And it's because they haven't defined limits, or they've just exceeded what's available, and then that can take time to debug. And that's where limit ranges come into play. You can create a limit range, which is a namespace resource, which will define defaults that will be auto-assigned to every container in every pod that gets scheduled in that namespace. But that's also, not necessarily ideal. Like, it's a good catch-all to ensure that you're tracking everything and defining resources and limits, but you also probably don't want the defaults all the time, so it's something to be aware of. And then network policies, another double-edged sword. If there are constraints around which pods should be talking to which other pods, then network policies are how you do that, because the default in Kubernetes is everything and everyone can talk to everything else, which is fine in dev, but if you're trying to achieve any sort of segregation, then you end up implementing these, and anyone who's dealt with a misconfigured network policy might know that they can be kind of tricky to debug, and when things stop talking to each other because some policy change, that's going to lead to instability. Stateful applications, I could talk about this whole talk, so I'll just gloss over it, but if you're doing things wrong, you're going to lose data, and there's entire solutions that I would recommend you probably look at, because if you want to roll your own in-house, you have to understand snapshot controller, backing up your persistent volumes, best practices around stateful sets. There are paid tools like Portworx that do a good job there, and open source solutions, but the long and short of it is if you have a stateful app and you haven't configured some of these other things and it gets evicted, then you're in trouble. Lastly, logging and monitoring. This one's just obvious. You need to know what's happening in your cluster, and by default, Kubernetes doesn't have a cluster level logging solution. So a vanilla Kubernetes cluster, you're gonna lose logs over time. Not everything's retained. When a pod gets killed, the logs for the totality of its lifespan are lost unless you're aggregating somewhere upstream. So, Yeah, and then one last thing is just that resource quotas can be scoped, and that relates to priority classes. This is just getting a little bit deeper. If you want to be defining quotas in a namespace, but you don't want to be applying those quotas equally to all the workloads, you can stratify it by priority class, for example. So that's another kind of more advanced usage with resource quotas. Okay, so now what can we start to talk about for how to achieve stability? Node problem detector is one of our 3 heroes that we'll talk about shortly. But what it does is, at a high level, is performs real-time health checks of low-level processes that would normally fall beneath the kind of observability of the Kubernetes control plane. And it can be useful to understand the health of things like the container runtime that you're running on your nodes, the kubelet, and other things. And you can surface events and node conditions which would tie into other alerting systems or even automated remediation systems. And then for topology management, there's a whole suite of different solutions. Cluster autoscaler, vertical pod autoscaler, and cluster proportional autoscaler all fall under the the Kubernetes parent project, the auto-scaling, sub-project within Kubernetes. And I'll be talking about cluster autoscaler a fair bit, but I'll just touch on these others first. So a hint, if you're trying to understand your workload, is to use vertical pod autoscaler with the off mode. So it has 4 modes. And by default, like its auto mode is it'll actually adapt your workload based on the resources being consumed. But that's actually a disruptive behavior, because if your initial spec is not in alignment with what's being consumed, like maybe if you're running a Java app and it's using a lot of memory, then it'll actually get bounced. So the API server will resize the deployment, and it'll do a rolling replacement. So there's downtime potentially, which is disruptive. So I have a link here, and I can share these slides later, but there's an open pull request to take advantage of a new Kubernetes feature as of version 1.27, which is in-memory vertical pod scaling. So basically the ability to patch the, online patching of CPU and memory specifications without having to do a rolling replacement of that workload. And you can, like I mentioned, you can run VPA in off mode, and it'll purely generate recommendations for how to size your workload, but it won't actually do anything disruptive. So that can be a good way to, if you're trying to figure out how to right size the things you have in your cluster, you can do that. The recommendations will just show up in the status field of the resource, and you can pull that out later and then subsequently change your manifest. Keta is another thing that if I'm giving a talk about Kubernetes scaling, I kind of have to mention. So it stands for Kubernetes Event-Driven Autoscaling, and it's also a whole talk unto itself, but it basically builds off of the horizontal pod autoscaler, which is a native Kubernetes primitive, and allows you to scale based off of external metrics. It also can perform behavior, like it has scalers that relate to internal cluster state, but primarily it integrates with dozens of external systems like AWS, all the public clouds. For instance, like a SQSQ, you might want to scale based off of the queue length metric, and it supports scaling to 0, which is cool. So if there's no messages in that queue, you can bring your deployment down to 0 replicas and then bring it back up accordingly. Then with regard to internal scalers, there's 2 worth mentioning, which are the Prometheus scaler and the cron scaler. So Keta can basically just scale workloads based on a fixed cron schedule, which if you're trying to operate workloads on a particular, follow the sun model or what have you, then that can be useful. And then the Prometheus scale will let you scale using cluster internal Prometheus metrics. So that's Keta. Cluster proportional autoscaler is in beta. It's kind of an interesting concept, though. It's basically you take a fixed allocation for a workload, and then as the cluster size changes, then the number of replicas for that workload and also the requests that they have will be scaled out proportionally. So if it had basically a request for 1 CPU and there was 1 node in the cluster, and then you added a second node, it would go down to half a CPU, and there would be 2 replicas, 1 on each node. So it's kind of an interesting concept, but it's in beta. And then the other final building block is Descheduler, which is one of our other 3 heroes, so we'll hear a lot more about it. Is anyone here familiar with vSphere DRS? Yeah, so distributed resource scheduler. I would say that Descheduler is basically analogous to DRS. A lot of people come to Kubernetes and they're wondering why there isn't a solution to automatically rebalance workload, and that's where Descheduler shines. All right, a few more building blocks. So policy enforcement, another big change with Kubernetes, not so recently, but as of version 1.25, they deprecated pod security policies in lieu of, well, now the new thing is pod security admission and pod security standards, but they're sort of woefully insufficient for any advanced use cases. There's 3 buckets, baseline, privileged, and restricted. So privileged is anything goes, restricted is you can barely do anything, and then there's sort of a midline option, but this doesn't meet the needs of a lot of enterprises, so what they end up doing is just disabling this completely and then going with a policy as code solution, like Caverno, OPA, JS policy. I'm a big fan of Loft Labs, that's why I threw in JS policy, but it's not as mature as the other 2. I would recommend Caverno if you aren't already using Rego, which is what OPA uses. Caverno is the most kind of Kubernetes native, and it's not quite as mature as OPA, but it doesn't require using Rego, so that's nice. But these just allow you to define very granular access control policies via webhooks, and it's just way more granular than pod security standards. Logging and observability, this, everyone knows about Prometheus and Grafana, I think, or if not, I'm sorry, but it's very common. And you need cluster level logging, like I mentioned on the previous slide. FluentD is an open source project that does a great job of that with the sidecar model, basically uploading all the metrics for all of your pods to a central location for querying. If you don't know what's happening when your pods are dying or things are crashing, then you won't be able to debug anything. So that's something that's mandatory in production. And then if you think you're doing everything right, or at least you think you're doing a pretty good job and you want to understand whether you're able to actually live up to the SLOs that you claim to provide, you might want to start playing with chaos engineering. Chaos Mesh is a project in that space that can basically just break things in your cluster. It can simulate node failures, take workloads offline at random, all sorts of different things. And of course, you'd simultaneously monitor uptime for all of your mission critical services. Okay, on to the heroes of the story. The first one is NPD, the node problem detector. This is also within the Kubernetes project, so it's open source and has been seeing more traction recently. Basically, you can install it as a daemon set. You can also just run it. In some cases, it's best to have it running directly on the nodes, but that's a little bit more complicated for provisioning. Although the advantage in that case is that it's not subject to the availability of the container runtime interface, which it's actually monitoring. So it kind of, in a lot of senses, makes sense to do that. It's just more work. But what it does is it submits events and node conditions to the API server, and it also can export metrics. So it has a concept of exporters. The default, or the kind of the main use case, would be to export events and node conditions to the API server, but you can also export metrics to Stackdriver and Prometheus. The events are for basically less severe or temporary issues, and then node conditions are interesting because they tie into the sort of synchronicity of these 3 projects, which we'll talk about shortly. But if you set node conditions on nodes, that can inform Descheduler to basically take those nodes or take workload off those nodes, and then Cluster Autoscaler can kick in after a certain point and decommission the node completely. So that is node problem detector. And a little bit more about it has a plug-in system. So the system log monitor monitors logs on the nodes where this is running. There's a kernel monitor and a container runtime monitor. And one of the example node conditions that would be generated by the kernel monitor would be a kernel deadlock. So basically this just means you have a list of node conditions that you want to set on nodes, and you set those conditions when you find logs in certain files matching certain regex patterns. But this can be useful for instance, detecting that a kernel deadlock happened on a node and then annotating that node with that node condition, which can then allow you to take action upstream and realize that that node needs remediation, because you might be able to react faster in that case versus just waiting for the node to completely die and the kubelet to stop responding. The health checker monitors the kubelet and the container runtime interface, so Docker or containerd, and likewise can produce conditions on the nodes like kubelet unhealthy, container runtime unhealthy. Then there's a custom plugin which allows you to basically just run any shell script you want, and they have an example in their repo for basically indicating that a node has an NTP misconfiguration. So it's very flexible, anything you could do with bash, and any condition you want to is the other thing worth mentioning. These are just examples, but you can come up with your own that are meaningful to your own organization. And then lastly, the stats monitor. By default, it just populates metrics that are exposed via a standard Prometheus scrape endpoint, and they're for storage, CPU, memory, all the typical things you'd want to know about the behavior on that node. And they can also be exported to Stackdriver. All right, so the second hero of our story is Descheduler. So it's basically DRS for Kubernetes, or if you're a vSphere fan, you can think of it that way. But what a lot of people don't know is that the scheduler doesn't actually evict pods for rebalancing purposes. It just does one-time scheduling up front, and then you get what you get. And in a lot of cases, that's fine if the cluster isn't experiencing any disruptions. But what might happen is that a node goes offline, and you basically have all of your workload on one of your nodes, and it's way overutilized. And then if you introduce a new node because your original node failed, nothing happens. You're going to have to manually go through the effort of reallocating workload or bouncing pods. So Descheduler will do that for you. This prevents bottlenecks, enhances efficiency, and can save you money. So it has a bunch of different strategies we'll get into, because there's different ways you might want to use it. But that's Descheduler in a nutshell. And you can install it like anything else in Kubernetes world. It has a Helm chart. You can run it in different modes. In the demo, we'll be seeing it running as a cron job, so it runs every 1 minute. You could just run it continuously, though. So 6 default policies that ship with Descheduler are here, and then you can also write your own, but these are just sensible defaults that you might get value out of. They're all pretty self-explanatory, but low node utilization means Descheduler will detect how busy nodes are, and if it deems them overutilized, it'll evict pods to try to reduce the utilization. The goal being to balance the workload across the entire cluster. And then high node utilization is the opposite, so you want to detect it wants to detect low utilized nodes and then evict workloads off of them to try to bin pack the workload, basically. And then that ties in with Cluster Autoscaler, because if you have a Descheduler configuration of that nature, then Cluster Autoscaler can start taking those nodes offline when there's so few pods on them that it determines that it's okay to get rid of them. And then I'm not going to dig into the anti-affinity stuff, but it's there. And then this last one, remove pods violating node taints. This is where the sort of trinity of these solutions comes into play. So right now there are limitations, but there's been active work on this linked pull request here in the last few months. Basically, what happens today is that the node controller in Kubernetes will only mark a node with the no schedule taint if certain conditions are set, which are sort of the default conditions that are set by the kubelet. So PID pressure, memory pressure, disk pressure, etc. And in that case, if that taint is applied, then Descheduler can remove pods with the no schedule taint, and that's super useful. But what we want to do is use NPD to set node conditions that are not the same as these kubelet-based node conditions. We want to talk about custom things like a kernel deadlock, and that's not quite ready today, but it should be merged soon. And at that point, we'll be able to leverage these 3 tools together. And it's not that Node Problem Detector isn't useful today, it just can't specifically be used to achieve that goal. All right, cluster autoscaler. So this runs on the Kubernetes control plane, typically in the kube system namespace, and it has integrations with all the major clouds. And if we're wanting to do this bin packing thing that I've been talking about, one thing to consider is how you've configured the node resources fit plugin for the kube scheduler. By default, it'll use the least allocated strategy. So this is how the kube scheduler decides where to put incumbent workload. It'll pick a node that's has low utilization. But if you choose most allocated, it'll do the opposite. And then that just basically increases the aggressiveness of your strategy for bin packing workloads, because descheduler will have to do less work in that case. And what it does at a high level is just changes the sizes of the node groups that make up your cluster, whether that means adding or removing nodes. And it's configurable through annotations, as well as a lot of other options I'm not going to get into, but some of them are good to know about. Like if you want to prevent a node from being taken offline completely, you can give it the scale down disabled annotation, and then pods likewise can be protected with the safe to evict true or false annotation, and daemon sets with the enabled DS eviction. And then another thing is the pod priority cutoff. So some workloads you might just want cluster autoscaler to disregard completely, and you can do that by setting a priority for those workloads that's beneath the cutoff. And that cutoff is configurable, but it defaults to -10. So you'd want to have a priority class of like, cluster autoscaler ignore, set that to -15 or whatever. And then you could throw 30 pods with that priority class onto your cluster, and cluster autoscaler wouldn't, even if some of them are pending, it wouldn't increase the size of the cluster. And how exactly does cluster autoscaler do what it does? Well, it depends on whether we're talking about scaling up or down. But with regards to scaling up, it has this concept of an expander, and there are a few different strategies for expanders. But the gist of it is, if there are any pending or unschedulable pods in your cluster, then cluster autoscaler will try to make a decision about how to add capacity to one of your node groups. The default is random, so a lot of clusters don't. Well, and also node group isn't like a Kubernetes native concept. There's no primitive called a node group. This is more meaningful with regard to like managed Kubernetes in like for instance GKE or AWS. A node group would correspond to an auto-scaling group in AWS or a managed instance group in Google. But then it also relates to cluster API, which I'll talk about a bit. But yeah, you can get complicated there, like considering price or priority. For instance, if you have like a GPU node group and you want to make sure that new nodes that get scaled out aren't GPUs because you don't want to spend a bunch of money, there's ways to do that. And then cluster autoscaler scales down nodes when certain things are true. So all of these things have to stay true for, by default, 10 minutes. You can configure that threshold as well, but basically a node has to have no blocking annotations, it has to have all movable pods, and the sum of all of the resource requests for all of the containers and all the pods running on that node has to be below another threshold, which is configurable. And then for a pod to be movable, that ties into pod disruption budgets. So by default, like all the pods running in the kube system namespace are considered unmovable unless you've specified a PDB that says, no, actually it's okay, you can evict these pods. So it can get a little complicated, and you might be in a situation where you're wondering why cluster autoscaler won't scale down your node, and these are things to think about, and we'll see a demo of when and why that wouldn't happen. Lastly, yeah, it's compatible with 25 plus cloud providers and cluster API, and I'll talk a little bit about an example architecture with cluster API. So for those who aren't familiar, cluster API in a nutshell is that you do declarative orchestration and provisioning of Kubernetes clusters from within a Kubernetes cluster using custom resources. So the management cluster is where you would apply these resources, which define the specification for your target clusters that you want to provision. And then there are different cluster API providers for different backends like vSphere or AWS, any cloud, any infrastructure provider you can name. There's probably a CAPI provider for that. And so here in this reference architecture, we would use Cluster API provider Helm to basically finish off the provisioning process, because one caveat with Cluster API is that out of the box, you don't get a fully conformant Kubernetes cluster. You get a cluster that has everything it needs but the CNI, which is kind of, you know, unfortunate. You have to get a CNI in there somehow before you can start scheduling all of your other application workload. And that's where the Cluster API provider Helm comes in. It's basically an add-on system for Cluster API that will allow you to specify Helm charts to put in on top once the cluster comes up. And then you might layer in the rest of your application workload with Argo CD via like a GitOps approach. This is just a high-level picture of Cluster API, but Cluster Autoscaler in this case sits on the management cluster, and that's also configurable. It could be on the workload cluster, or it could be somewhere else completely. But Cluster Autoscaler really shines with CAPI because you can do things like scale to 0 and just perform declarative management of, you know, a whole fleet of workload clusters. And we'll look at a little bit of YAML. Basically, we have a deployment for Cluster Autoscaler, and it's in kube system. And what we have here is the kube config for a theoretical target cluster, CAPI dev, and it's mounted as a secret into this Cluster Autoscaler container so that it can talk to that target cluster and understand what's going on within it. And then there's this concept of node group auto discovery. So like, you know, what is a node group? It's not a Kubernetes primitive, but in this case, we're telling Cluster API to just consider all of the machines within this CAPI dev target cluster as one node group. But that can be more nuanced. You can break it down by labels or namespaces, etc. All right, so we have this deployed in the management cluster, and all we have to do is add a couple annotations to the corresponding CAPI resource that was reconciled on the management cluster to create the target cluster. So we just define the minimum and maximum size of that cluster, and in this case, 1 and 10. And there's a bunch of different ways you can define clusters in CAPI, so it could be a machine set, deployment, or pool. And I won't get into the differences, but basically these are custom resources that define the size of the target cluster and the types of nodes that will comprise that cluster. Some CAPI providers have native support for scale from 0, but even if they don't, you can add additional capacity annotations that basically tell Cluster API, even though the provider doesn't support scale from 0, this is basically the size of the node that will get provisioned in terms of its CPU capacity, memory capacity, storage capacity, etc. And when you annotate your machine set, for instance, with all of that information, then Cluster API has all the information it needs to understand when to add and remove nodes, which is pretty cool. All right, let's make them work together. All right, so basically I have taken a few shortcuts. I have an environment in Google Kubernetes Engine that I'll show you here in a moment. And the first thing I'll do is just deploy, I have a single node running in it, and I'm gonna deploy enough pods to create resource pressure. Then we'll watch as Cluster Autoscaler provisions a new node, and subsequently Descheduler will rebalance pods to have an even spread between the two nodes, which wouldn't happen by default. And then we'll update the descheduler config to do the reverse, so basically to bin pack all of our workload, and I'll also delete some of the pods that I created to initiate that resource pressure, and then we'll watch as the pods are all allocated on a single node and Cluster Autoscaler deprovisions it. And then lastly, we'll write some messages straight to the kernel message log, and we'll watch as NPD updates the custom conditions that I've configured, and we'll see that in the Google console. This might be tricky. Okay. before I start doing things in K9S, I can't see this here, I can only see it there, so that's weird. Here's my SCaLE 21x demo cluster. I've got one node, and I'll just show you a few GKE specific things first. There's this concept in GKE of an auto-scaling profile, and by default, it won't be set to optimize utilization. This basically means it tells cluster autoscaler, because there's a managed cluster autoscaler that's being configured and operated by Google on my behalf, so I didn't have to install it in my cluster. It's as simple as just clicking a button in GKE to enable this feature, and now because I have this profile enabled, it will be aggressive in terms of decommissioning and commissioning new nodes. It just happens faster, so it reduces some of those thresholds. And if I go to the nodes and I click into this default pool, basically, I'm just trying to show you that it's as easy as a click of a button with GKE, but it's being really slow. And I've configured it to have a minimum of 0, maximum of 3 nodes. And instead of having you watch that spinner, I will just move on. So up top here, I'm just showing all the nodes in the cluster. And then down below, I've got all the pods. And I've created a bunch of pod disruption budgets. So I mentioned earlier, certain things will not get evicted by default unless you create a PDB. So things in Kube system are considered immovable. And so unless you apply these PDBs, then you'll see cluster autoscaler failing to scale down your environment. That's why these are all here. And I've got Descheduler installed. And it's running as a cron job. So if I get the cron jobs, you can see it's scheduled to run every 1 minute. And if we look, I've applied an annotation, which basically says cluster autoscaler should not care about any of these descheduler pods, so that they don't get terminated right away as the job's complete, so they start to accumulate. And therefore, I just want cluster autoscaler to ignore them so that it can be as aggressive as possible in decommissioning nodes. And then I've also got NPD running. So I only have one node, and it runs as a daemon set. There we go. So we can see node problem detector is running. And so far, it hasn't really done anything other than it checked for a bunch of conditions and said they're false. So we can see by going back to the nodes and describing this node and going down to its conditions, we can see node problem detector has said, typically you wouldn't see a lot of what we're seeing here, like no corrupt Docker overlay, kernel has no deadlock. These are all things that are added by NPD based on the fact that it hasn't detected any problematic log lines. And then we have the standard conditions that the kubelet creates, like ready, memory pressure, disk pressure, etc. And lastly, we have descheduler configured via this config map, which is unreadable for humans, so I won't show it to you that way. But this is the current descheduler config. And I'm not going to go over it in excruciating detail, but basically I have low node utilization enabled, and we have some thresholds. So any node whose total resource consumption falls beneath the specs here, and it has to be for all 3, will be considered underutilized. So fewer than 20 pods, less than 100% CPU utilization, less than 10% memory, that's underutilized. And then any node that has all of those same metrics above these values will be considered overutilized. And if that's the case, descheduler will say, hey, this node, if it's overutilized, it'll evict pods to try to reschedule them onto less utilized node. So that's what we have now. And I'm going to just create some arbitrary workload. And pretty soon here we will see pending pods. So now that these are pending, that's going to trigger cluster autoscaler to scale out the capacity for the node group. We only have one node group, but it won't take very long, and then we'll have another one, and we will change the policy and flip it. We'll wait a second to let dscheduler balance everything, but let's give that a minute, and maybe while we wait, this would have loaded. Yeah, so in Google or GKE, it's as simple as just ticking this box and specifying your thresholds. This is sort of similar to the annotations I was showing you for Cluster API, but it's just you know, white glove integration. And you can view the cluster autoscaler logs in Google's Log Explorer. What I'm going to do is hopefully show you the scaling decision that gets made. So what was that? That's hard for me to read from here, but I think that just happened. So is this, can anyone see this? Is this, how's that? Okay. So we just triggered a scale up, cluster autoscaler triggered a scale up because it saw this pod that was pending. And if we go back, yep, it's there. And not only that, but it's actually balanced. So by default, we would have had 40 some odd pods on that first node, and I apologize because I was being too slow and we missed it, but we can go back and find it in the events. So if we look for, well, let's just go down to the latest events. So we see a bunch of evictions based off of taints. So these, everything you see here with taint manager eviction, this was descheduler evicting workload because a node was tainted. But let's just go to the descheduler pods and look at some of their logs. So the last one ran a minute ago. Okay, it didn't do anything useful a minute ago. We might have to go further back. Well, maybe I'll just show you on the scale down because I was a little too slow. But the gist of it, as you can see, is that this rebalance happened. What I will do now is flip the policy. So if I show you the descheduler high policy, it's just the inverse. We have low node utilization disabled, and we have high node utilization enabled, and that will cause the workload that we have currently balanced to become bin packed. So I will apply that. Oh, that's not what I want to do. So that's been reconfigured, and then I'll go delete a few of these things. So the high memory and the low CPU deployment, I'll just kill completely. If I don't get rid of them, then there'll still be just too much going on in the cluster for it to be deprovisioned. And then the high CPU deployment, I'll just scale it down to 1. And what we should see soon is that the cluster autoscaler will add a condition to the node that gets rebalanced and mark it for deletion, and it'll get taken down. but this time we'll watch Descheduler hopefully do something interesting. So Descheduler detected an underutilized node and evicted some pods. And you can see the ratio has shifted. And if we give it another minute, that ratio will shift even further. So we have to sit tight for 30 seconds, but once the number of pods on the node gets down to about 9, it'll have sufficient, the sum of the resource and requests, so the CPU and memory requests on that node will be sufficiently low that it falls beneath the threshold the cluster autoscaler considers it a candidate for deletion. And then another thing we can do is just look at what's on that node. So fortunately for us, these guys won't get considered at all because of the annotation that I added. And then what remains is almost entirely default pods that are going to be there all the time because it's cube system workloads for the control plane. And this is, you know, just again to reinforce where the PDBs come into play. So if I didn't have the PDBs, this node would be blocked from a scale down event just because these workloads are here. But because I do, it was able to update that node. And if I go back, it is starting to kind of thrash a bit, but if we give it another minute, I would say it will mark that node as a candidate for deletion. And while we wait, I'll just tee up the final thing I want to show you. Before we do that, I'll just show you one more thing, which is some different cluster autoscaler logs, which is sometimes cluster autoscaler isn't making a decision, and you can debug that by expanding some of these log lines where we see no scale down. So, okay, why did no scale down happen? In this case, there was no place to move pods. So that's one example of why a scale down event wouldn't occur. And this is another example, which I didn't touch on earlier, which is that you don't want to ever have pods in your cluster that aren't controlled by a replication controller. So if it's not backed by a deployment or a stateful set, those pods of that nature can also block scale down events because there's no guarantee that workload will get rescheduled. So cluster autoscaler is hesitant to take a node down if that type of workload is found. All right. So if there's a pod that's been scheduled on a node that was just an ad hoc pod, like you just did kubectl run nginx or whatever, and it's just one-off and it doesn't have a parent controller, then there's no way for cluster autoscaler to know if it kills that, if it evicts that pod, will it get recreated? So in that case, it'll not initiate a scale down. That node, any node that has that type of a pod of that type. All right, there we go. Mark the node as to be deleted, and now it has a bunch of different taints. And in a moment here, it'll get deleted, but I won't make you watch and wait. I'll move on. Google's killing my demo. All right. So I want to make sure I get the one that's not about to get killed. And I'm going to dig into the underlying VM instance and open an SSH connection. Let's just see while we wait. Okay, it's still there. And Okay, it's gone. So yeah, changing the policy caused the bin packing to occur, and cluster autoscaler took that node out. And I will demo one last thing really quickly. I might move on to my takeaways while we wait for this, and then circle back. Well, we have 10 minutes. Any questions while we wait? Oh man. This was working like during the last session. I don't know. Oh, here we go. Yeah, totally. So I will elevate, and then over here. I did that earlier. Okay, we're gonna tail the NPD logs, and we'll just see instantaneously when we write this message into the kernel log that NPD picks it up. And I think I copied some other, no, okay, I got it. So I basically simulated a kernel panic, or sorry, a kernel deadlock, and NPD picked that up. So obviously this is contrived, but if that happened, NPD would have noticed. And if we go to the node and look at its conditions, it now has kernel deadlock true. And if we cut back over to Google, we can actually see that got surfaced in their UI. And now things are not good. So that's just one example of what you can do with NPD. And shortly here, in a few months, hopefully we'll be able to apply taints to nodes directly based off of conditions created by NPD, and then Descheduler can act on those taints. All right. So we want stable Kubernetes clusters, and there's a lot of things getting in the way of us achieving that, but there's also a lot of ways we can achieve it. It just takes understanding a lot of these Kubernetes primitives and the pieces available to us in the ecosystem. So configuring things like NPD, Descheduler, and cluster autoscaler can get us there. And we should be proactive by understanding how to configure these tools and understanding what they have to offer. If we combine that with pod disruption budgets, resource quotas, and limit ranges, we will have hopefully a more robust cluster. And then lastly, if we can leverage the power of the API server to provision our clusters declaratively using cluster API, then I think we're in a really awesome place. And shameless plug, that's what we do at Spectro Cloud. So we're a Kubernetes management platform. We have an abstraction called a cluster profile, which you see here, which models the cluster, including Descheduler, cluster autoscaler, and NPD. And you can deploy this with a click of a button to basically any cloud. So it's built on CAPI though, which is we upstream a lot of stuff to the various CAPI providers like CAPI vSphere, the cluster API provider for MAS we contributed. So if you're interested in CAPI and autoscaling, that's us. And thanks for your time.
Thanks, Tyler. Does anybody have any questions? I've got one. Is it possible to implement your own custom plugins to do these health checks of things that are running in the cluster, or even health checks for cluster nodes if they're on like physical hardware, for example?
Yeah, so NPD's custom plugin, custom monitor plugin, I believe, just supports any shell script. So if the shell script exits with this particular status, it'll set a particular condition to either true or false. So you can do that with NPD, and then Descheduler is also highly extensible. Like I just showed the 6 out of the box default policies, but you can write your own. And cluster autoscaler, not so much. But yeah, there are ways you can, everything with Kubernetes is kind of one of the cool things about it is it's very extensible.
Okay, anybody else got a question? Okay, join me in thanking Tyler for a great presentation. Next in this room in about 15 minutes, we actually have another talk on Kubernetes resource management, so that if you found this talk useful, there's a fair chance that the next one might be, you might find it interesting as well. Thank you for coming.
Thanks, everyone. Thanks, yeah, absolutely. First ever conference presentation, so.
Yeah, this is a little unusual if you've been on the conference circuit, because this is an independent one, whether you knew it or not. Like, it's pretty inexpensive for people to attend. Before COVID, it was a lot bigger than it's running now. When it comes back, but it peaked at about 4,000 attendees.
Oh wow!
It's the biggest independent open source conference in North America.
Very cool.
People can come here for like $50 compared to what.
Oh whoa! No, I didn't realize that.
Go to the Cube conference.
Yeah, an arm and a leg.
Props for the live demo of all the Wi-Fi. That was great.
Thanks. Yeah.
Actually worked out okay.
Yeah, I don't think you needed to apologize that much. It looked pretty good. The people who got burned here, this is unfortunate. We'll have to give warnings going forward, but people were using code spaces and things like GitHub, and they all came out of the conference internet connection, and they started throttling. So it's almost like in workshops, there were people counting on using sort of some of these free solutions and giving out links, and some of that didn't go well in the end.
Was that some of the workshops like this conference?
Yeah.
I was sitting in with a hardware presentation.
I think code spaces is a way that Microsoft GitHub hosts essentially like VMs for it. But if they notice that a lot of requests are coming out of one block of IP, so apparently cut back the resource allocations to the point where it really bogs down. We got on the horn to ask them about it, and we even had some people here, but it took a while.
Hopefully I didn't talk too much about resource requests. I didn't realize these were
Yeah, they definitely are related. It's such a broad subject. In fact, it might be a true geek fest. I think you can put on a whole day of things related to this, and especially when you get into things like storage, and if you get into even resources that are sort of off the path on Kubernetes, and everything is pluggable. But if you have GPUs or something that aren't really architected right into the get-go, there are ways that you can do scheduling based on those resources. But I mean, all up to you to do much of it. Maybe to get their attention. It's quite a challenge. So it's intro level going up to pretty advanced topics that I think London can approach unsolvable problems. So So I'm the moderator. You can do anything from introduce yourself, and I'll do it for you. And I'd suggest hooking up just to make sure there's not some anomaly that
Absolutely.
prevents your screen from showing.
Yeah.
This mic seemed,
I noticed it wasn't really working. I can make do with this one if I need to. I mean, if we have time. If it wasn't working before, though, I doubt it'll be working now.
and I have cards to give you warnings, but you're the last of the day, so if you go over, it's not a big deal.
I still don't want to go over, but I appreciate it.
Water's here. They're good chocolates. They come from a local gourmet chocolate place. Okay. I'm going to pop out and use the restroom, but I'll be right back.
Is this thing on? Not yet. Just testing. Last presentation of the day. I'm surprised they even have it. I know, right? It seems like they went super late, but it sounds like Saturdays used to be really packed this week. Yeah? Yeah. Like this is past my bedtime by the time I finish this. Right. Is there still a giant crowd in front of the America's Got Talent or whatever that thing is? Oh, okay. I'm in Seattle. Yeah. Had the brilliant idea. I was working with a friend or a colleague really on sort of some ideas for some presentations, and was like, hey, we did the seed version of it, kind of a 15-minute thing of it in Seattle, and it's like, hey, we should submit for some KCDs. And then it's like, oh shit, we gotta stop it. I have to make it into a 40-minute, and then did all the work, and it's like, oh shit, this is now a 90-minute presentation. Now what do we do? To your point earlier, resources, you reach them at the very entry point to Kubernetes, one of the very first things you see because it's part of a pod, and then you dig down deeper and it's like, oh my god, there is so much underneath this entry point.
Well, the rookies, and I think to a larger extent, of inverted Kubernetes is totally sketchy. Couldn't find where it sort of works. Hello World, fine.
Hello World works great. Yeah.
Sadly, there are more stories of companies doing that, throwing it into production and having some bad days.
Yeah.
Even some mystery ones,
were lucky to have the direct flights, and that got me over. I was like, man, I love small airports. This is great.
Yeah, I think my favorites were that Collide AI event, day one. Yesterday, Corey Quinn's talk on Kubernetes. You're not familiar, he's sort of a comedian slash presenter.
Which one was, do you remember the title of his talk? Was it the last one of the day?
Bad ideas with
Yes.
Kubernetes.
Yeah, I didn't make I was there for like the intro slide. I saw that abstract and was like, I don't know what he's going to say, but he's got my attention.
Yeah, watch it on the recording. It's humor with satire where there's elements of truth in there. He's making points to basically ridiculing the complexities of Kubernetes. If you didn't know this, we record this with these security cameras. So
Okay.
the budget is low enough, we're not hiring an actual camera crew. But it will be published on YouTube by the conference room. So if you need to find your talk to give references to it, or send it out, it will be under Ballroom G, SCaLE, and the date. And then you can get a YouTube bookmark that has a starting timestamp to
That's great.
queue it up just on your own.
Nice.
But it should be on the air. Sometimes it's not.
So an advantage of having the last talk of the day is that start where I send you and then it's over.
Well, they throw the bit that it allows sampling, which I'm not in charge of that. I think you can probably spawn up your own edited one anyway. So your part, they intercept the feed right under the table. So the slides are decent, and then you'll be just a tiny superimposed on it as the
That's great.
resolution comes down.
Small as you can make it.
Hopefully you're not disappointed you did get the last slide, so maybe this will be
It's
the
okay.
strongest attendance.
It's one of those
After
things.
hearing you talk to quality, it's at least there, and then
I'm not worried. I was, Tyler was saying this was his first presentation at conference. I've done a couple, but it's been years, and I always forget. The reason I don't do presentations is for no rational reason. The lead up to them always stresses me the hell out. And so a small audience is totally cool. I think a lot of times just doing the research to be able to present on the topic is, for me, it's actually worth quite a bit because it forces me to actually understand what the heck I'm talking about.
I've been crazy about it. I was on the conference circuit, and I decided that was the motivation to learn things. So I did a thing, open source summit, talking on service mesh, because the lead time is 6 months. I figured 6 months, I can learn anything. I need to learn service mesh, but
Oh, you submitted
I
without
have the motivation of not embarrassing myself. I'm just going to go ahead and do it.
Oh, that's brave.
Actually, it was this idea that service mesh is made for use by Kubernetes workloads. And they had a thing just hinted at in docs saying that it's at least possible to put these plugins into general purpose VMs or physical machines that have them join the mesh. And at the time I was employed by VMware, it was really cool that you could link these up to general purpose VMs. And whether it would even work, I'm not even sure if it would work. Linux, since there are Linux packages that are being published by projects, there's no reason it shouldn't work. But I ended up calling the two leads of native service mesh and asking, should this work? Yeah, it should. Well, I'm thinking of doing a talk on it. Would you help me out getting it to work if it doesn't? And he said, sure.
Nice.
And so I went ahead and did it. And it worked out fine. But
That's great.
that was walking out on a mysterious.
Man, yeah, that's kudos. That sounds terrifying. I 6
I
months
did
is
learn. I
it
mean,
is
that-
it's plenty of runway, but yeah. One thing I did notice, again, it's been a long time since I've too long. There's way too many specifics in there because especially as you're cutting it down to a 40-minute talk, it's like, well, we actually can't fit everything we said we would. That's one.
Well, they don't really, I'm on program team for this conference too, so I read the things. And there's no feedback loop where you deliver wasn't all of what you said that anybody really enforces it.
Oh yeah, and I just,
It's kind of like what you're looking at. People do ask whether it's doable in the slot you have, because sometimes it comes up that what this person is going to address, no human being I'm aware of could cover this in 4 hours, much less.
and the audience couldn't follow it if they did.
So that does come up, and I think I remember yours was the fine name. It's sort of like just lay out the plan of what knowledge you intend. You intend to leave with the audience a few sentences of how you intend to get there, and that's it. You can quit. You don't have to. In my mind, embellishments of the speaker's credentials and stuff can be most of us who review. I think I'm also a program committee at the KubeCon conferences. Most people don't trust speakers own build up. I like to look at prior talks on YouTube and go do my own independent research and just ignore speakers put out there in their own bio. The bio goes into the program guide later, but I think effectively also because you don't want bias, for demographics or whatever. I definitely ignore them. I'm just looking at abstract. If the conference setup even lets me never see the person's name, I will do that.
Yeah, I'm not, this will be on target for the information presentation, but when I was looking at the abstract, I'm like, we mentioned a bunch of very specific things, like I said earlier. There's a tip of the iceberg in resources, and like, you were mentioning like GPUs and device extensions and so forth. You can go 12 different ways, and there's only 45 minutes in this presentation. Cool. Is this thing on yet? Sounds like it's kind of on. I'm going to get the height adjusted because part of this is going to involve me having hands on keyboard and I'm not going to be able to hold it. So actually that's as high as it goes. So I guess that's it. Cool. This is like the last 30 seconds before we officially hit 6:15 for the last talk of the day.
Okay, I think they're there. Join me in welcoming Reed coming down here from Seattle to give the talk on Kubernetes resource management. I'll let him proceed with introducing himself and let us know whether he wants to take questions during the presentation or hold them to the end.
Awesome. Yeah, thank you very much. I'll address that question thing up front. Since there's since it's such a small audience, I would say absolutely, move forward if you want to. Feel free to engage me during the presentation. It is timed without any interruption to last about 45 minutes. It might end up getting tweaked with your engagement, but I'm okay with that. So definitely feel free to ask questions during. A lot of it is going to be a live demo, not as live as Tyler's demo before mine. If you saw that, I was highly impressed, very brave, doing a demo over the Wi-Fi, live on a conference. My demo is going to be Minikube. It's going to stay on my own laptop because I don't trust the Wi-Fi. But definitely feel free to engage. So with that, welcome to Demystifying Kubernetes Resource Management, everything you've always wanted to know. All right, I'm going to take this off for a second, but we're afraid to ask. Let's do this. So agenda-wise, just going to give you an outset for how I'm planning on addressing this topic. I'm going to spend a little bit of time up front doing basically level setting and also kind of just making sure we're clear on the question of like why resources matter in Kubernetes. Most people who have done run their own clusters or run the platform probably have a pretty good idea of what the answer to that is, but I'll tell at least one anecdote that one of my colleagues and I have been kind of using as a basis for putting this together. And once that kind of baseline is established and we've kind of just reviewed real quick resources and limits and the basics, make sure everybody's kind of level set, the majority of the talk is going to be two hands-on kind of live experiments or demonstrations. One on CPU resources specifically and one on memory resources specifically. There are, of course, other kinds of resources in Kubernetes. I think I mentioned them in my abstract. And then when you start trying to trim a talk down to 40 minutes and it's the subject of resources, unfortunately, they didn't get a lot of airtime. They will get mentioned a little bit later. But it's mostly CPU and memory today. And there's a little bit at the end just talking about, okay, great, we talked about some of the, the problems and what happens during contention and so forth, and then just we'll spend a tiny bit of time talking about what can we try and do, what did my buddy Rafa do to try and point everything in the direction to do as well as you can given the realities of the resources abstraction and kind of what's going on there. A little bit about myself. My name is Reed. As was mentioned, I'm up in the Seattle-Tacoma area. I've spent about 12 years plus working primarily with IT automation problems. I've been doing Kubernetes for the last little over 2 years, I guess, now at this point. Prior to that, I mostly worked with Puppet. Love the transition, one declarative management tool for kind of more traditional single operating system Linux stuff into, hey, this is the same philosophy, but it just is more, it's more, what's the word where it means stuff doesn't change? I can't remember it right now. But enjoyed that. Outside of work, I think you were gonna, immutable. That's what my brain was going for. Outside of work, I like to do a lot of hiking, a little bit of mountaineering because Seattle is just a beautiful area for that. Try not to work too hard. I'd recommend the same. So getting started, the Kubernetes resource abstraction. Again, the level setting. Resources in Kubernetes are things like CPU, things like memory, things like ephemeral disk. That's another built-in one. Things like GPUs, not a built-in one, but it's the most common one besides those. And in Kubernetes, the idea is that nodes have resources. Pods to run, they need some of those resources. And your cluster is a whole giant collection of nodes, and Kubernetes' job is basically to figure out how to put pods on those nodes in such a way that all of their resource requirements are satisfied. So a little bit about, great, that's what it is, but question, why does it matter? Or sort of why is it worth kind of putting together a giant talk about? I say giant, it's 40 minutes. So story time. At Stormforge, I work closely with a friend and colleague. His name is Rafael Brito. And in 2016, he was tasked with leading a team at a large bank to implement a new Kubernetes platform. This platform was to serve a wide variety of internal customer teams. Rafa's responsibility was to provide the platform, but he wasn't the guy who was going to be responsible for running most of the workloads directly. Again, lots of individual people. He's just the platform manager. So this being early days for Kubernetes at the bank and him still figuring out how all this stuff works, his initial strategy for dealing with this idea of resource requests was pretty simple. He called it benign neglect. He figured that what he would do is he would use some built-in resources to try and point his users on the path on a path rather, by providing or suggesting some generous default request settings for CPU and for memory, and then step out of the way and let the developers figure out and manage and maintain kind of their own resource request settings all by themselves. Mind you, this was early days Kubernetes. It was not on a cloud. It was on-prem, and so auto-scaling wasn't really a thing, and clusters capacity had to be pre-planned to some degree and rationed. Okay, so he onboards the first few teams. Shockingly, within a couple of days, this is like not even the whole set of customers, just the first kind of the pilot teams, as you will. Within a couple of days, he started getting calls from people telling him that, or complaining that their pods weren't being scheduled due to a lack of resources, specifically mostly CPU resources. So he went to talk to his VMware team providing the nodes. They told him that he was averaging about 15% CPU utilization across the entire cluster. I think I've actually talked to a couple of people over the conference who told similar stories. I think 10% was sort of the number that I mostly heard. So 15 was actually, Rafa was doing pretty good. But in 2016, Rafa's policy of benign neglect had revealed one of two major problem categories that come from poor resource management in Kubernetes. In this case, it was cost from over-provisioning of resources for the workloads that you're running. The other major category of problem from poor resource management is under-provisioning. Arguably, that one's worse. Under-provisioning would have likely shown itself up in the form of poor reliability or unpredictable performance of the workloads that he was running. So he kind of got lucky with cost. It's expensive, but at least things were working. Not that everything was working because you couldn't schedule all the workloads. But moving on. So that's kind of just, that's one story. Almost everybody I talk to about this who's been doing Kubernetes a while has a version of that of their own. So it's not an isolated problem, but I wanted to give kind of at least one for people to latch onto. All right, so diving into resources, now that we know that they're important somehow for a couple of reasons, cost or reliability. Most of the slides I put up are going to be talking at one of a couple of levels of abstraction here. I've labeled them the Kube API, so the user-facing abstraction for requests and limits, the stuff that you see in YAML for the most part. I've labeled one kubelet, but really this is just nodes. Okay, great, a workload got to a node, or how did it get to the node based on resources? This basically relates to pod scheduling. And finally, I've labeled one of the layers C group, or C groups. This is basically, okay, great, the workload is running on the node, but it's going to have some implementation of that abstraction, and it turns out for CPU and for memory, it's basically all C group style stuff, and so sometimes when I'm talking about what's going on, it'll be at that level. There's a process running, it's on Linux, it's in a C, it has a C group, and so forth. Final bit of level setting, resource basics. Again, reminder for anybody who hasn't seen it, requests are the minimum resources a container is asking for guaranteed access to, and that is an input to the scheduler. It's going to try and find those requests somewhere across the cluster. Limits are a maximum that a container should be prevented from exceeding in the event that it tries. The two are not the same, so just wanted to emphasize that. And as I said earlier, requests are the one that matter in terms of allocation per the scheduler. The scheduler is going to try and make sure that it puts workloads on nodes in such a way that it never exceeds the node's total capacity. If a node has 2 CPUs, it's never going to, the sum of requests of pods running on that node are never going to exceed 2 CPUs. Scheduler never over provisions, according to requests. Over provisioning, and I'm kind of getting into over provisioning because resource management is really simple if you never over provision. So that's mostly what we're going to be talking about. Over-provisioning is technically possible whenever the requests and limits aren't equal, including when limits are not set. And for many workload types, including RAFAs earlier on, over-provisioning to some degree, for most workload types, there are exceptions, is usually desirable for cost optimization. So the focus of the rest of the kind of the presentation and the demos is going to be talking about like how to over-provision. Should we over-provision? Should we not over-provision? When and why? What happens when you do? The reasons are, you know, over-provisioning leads you towards some savings on cluster costs, but you're basically getting that by sharing resources to a degree in terms of who they've been allocated to. The other flip side is reliability. That's great. Resource exclusivity is the kind of the far end of that spectrum, but that costs. It can potentially cost quite a bit, and money has gotten very expensive in the last few years. So last slide before we kind of dive into a demo and start focusing on this question, is over-provisioning safe? What are the consequences of over-provisioning for CPU, and what are the consequences of over-provisioning for memory? I think that's about almost it for me talking without actually showing anything. So there's a couple of different ways to do demonstrations or philosophies. I think in the talk before mine, Tyler started by saying, here's what I'm going to do and what I expect to see. And then he did it. I'm going to do the flip side. I'm going to run an experiment without necessarily telling you what I expect to happen up front. Feel free to kind of make your own guesses as we go. After it's done, I'll explain what happened and sort of what went into it. But I noticed in the last talk, there's 2 philosophies here, and I've definitely chosen the opposite one. We'll see how this goes. So my lab environment is Minikube. It's running on my laptop. At least I hope it's still running on my laptop. I'll tab over in a second. We'll find out. And I've got a monitoring stack because I want to show you guys actually watching what workloads I have running and what resources they're using as I do it. And I've also got a dedicated node to run these resources on. This is important because I can kind of force exactly the resource contention and allocation situation I want. In a real cluster, this is a complex system. You don't often get to force everything into kind of a magnifying glass and see it as where you want to see it. So that's one note is I'm showing everything in a microcosm, but when you blow this out into a complex system, the interesting thing is you can't really predict exactly what's going to happen all of the time. Can this still work? That still sounds like it's working. Excellent. All right. I also wrote myself a little driver script because I'm terrified of typing too many kubectl and yq commands. And so what I'm going to do is I'm going to do go run ./demo.go. I'll show you what it does for me, help file. I've written out a bunch of different steps. I'm going to start by basically walking you through the inspect nodes point to just prove what kind of cluster I have running. Actually, let me clear that out first. So I have a demo cluster. If I run kubectl get nodes, I'm going to exclude my control plane node, which is running my monitoring stack as well. And we see the one node, demo M02, that's my test node for workload clusters. It's ready to go. Because I'm talking about resources, I want to show you how many resources this node has. I'm going to show you allocatable and capacity for this node. Capacity is basically the raw measure of this node's resources. It's got 2 CPUs, about 8 gigs of memory, and I'm going to ignore almost everything else for the purposes of this talk because I'm already 25 minutes in. And actually, no, I'm not. I started at 6:15. Okay, whew, I'm going to slow down. We're fine. All my practice sessions, I started on the hour. So capacity. That's the raw resources the node actually has. The difference between capacity and allocatable is the node, typically kubelet reserves a little bit of capacity for itself and for potentially other system level resources so that when workload pods get scheduled onto it, they're not going to be interfering with that sort of like reservation slice. Allocatable is therefore typically different than capacity. This is Minikube and a dedicated worker node. I realized after I put the talk together that Minikube doesn't do that. Minikube is basically just giving the entire capacity available for running workloads as well. This is bad. I'll explain why when we get to the memory demo. All right, so that's just kind of an overview of the environment. So I mentioned, let's see, that's the overview. Moving forward, experiment number 1, focusing on CPU, resource settings, and CPU contention. Again, we'll do something interesting and then explain the results. So for the CPU demo, I'm basically going to start by loading up some resources. I also realized watching Tyler's demo that I should probably learn K9S. I don't operate that way. I just run kubectl commands. Maybe that's weird. I don't know. Should do a poll. Seeing some head shaking. That's good. So I've got a directory full of resources, CPU. Basically, I'm going to create a couple of services because I got to talk to them, and 3 deployments. The first deployment is what's called a best effort workload. It has no requests and it has no limits. Second deployment is one I called requests with no limits. So it's a burstable workload. And the last one has requests, but it also has limits. They're not equal, so it's not guaranteed. I'm not going to talk a lot about quality of service stuff till we get to memory, but just a tag in your head if you're familiar with that. So they should be running by now. We can see that they are. They're all up. Just to confirm, they're all running on the same node. This is important for the sake of the experiment in doing science, because if they were on different nodes, this would not be very interesting, or at least I couldn't force contention. And then I said some have requests, some have limits, some don't. Let's take a look at what those are. A lot of these commands, by the way, I've said I'd script it because that's way too much YQ. I don't want to show you all of the YAML, but I do want to show you the actual YAML. So here we go, kubectl get pods, and then I'm just going to ferret out just the resource requests for this thing. So there's that best effort one. It's got no requests for CPU, as expected. For the ones that have requests, they're both requesting 500 millicore, and the last one has a limit set of 1 core. I promise I won't keep it all CLI and YAML, so the next piece will actually take a look at a graphical interface. I'm going to show you the monitoring stack so we can kind of watch the consumption of these as we go. I got to start that port forward, so let's run that down here. That's forwarding. And then this URL is what I want to take a look at some workloads. All right. I think Tyler also mentioned Grafana and Prometheus, cAdvisor, wonderful tools. Almost certainly heard of them if you're using Kubernetes. At this point, if you haven't, definitely check them out. This is, let's switch over to CPU. This is basically just a page where I can see how much CPU these workloads are using and how much memory they're using on this node. They're currently using next to no CPU and have a baseline set of memory requirements. These pods, by the way, are a tool called Resource Consumer. Resource Consumer is a part of the Kubernetes project. It's used for testing. I assume because kubelet cares about resource usage. I actually don't know what they use it for. I just know what I use it for. And what it lets me do is it lets me tell these pods exactly how much CPU and memory to consume, just kind of on a whim. Before I switch over, I'm going to try something. I'm going to switch this to just the last 2 minutes because we're going to be looking at really close events here. So the next thing I'm going to do is I'm going to load these things up with some CPU usage. Every single one of these pods is going to have a baseline consumption of almost half a core. Again, the node has 2 full cores available. Those are the curl commands, but basically it's 450 millicore baseline consumption for each of these. So we can immediately over in Prometheus see that consumption begin. So total CPU usage over here is about 1.4, and I've got a stack chart showing each of these workloads. So they're each consuming right around 450 millicore. No contention so far. They're all under request if they have requests, and the node has available CPU. Okay, let's make something interesting happen. What I'm going to do is I'm going to have one of these containers start over consuming. The one that has no limits, I'm going to ask it to consume an additional 2 full cores of CPU. Remember, the node only has 2 cores, and it's currently already using 1.5 of them. So when this pod starts trying to overconsume, something's got to give. Either it won't be able to do that, or it'll take resources from one or more of the other pods. If it does, which ones it can take it from and how much. I'm just going to fire that off and see what happens. All right, so that's running. And this is refreshing every 5 seconds, but I'll hurry it along a little bit. Okay, so we just saw that consumption start. The blue one on top is the overconsuming node, or pod. As it starts, this will run for about 15 seconds before resuming normal baseline 450 millicore. Note what happened. So this top one, it's consuming up to the node's limit of close to 2. There are some measuring artifacts. If it goes above 2, it's not actually using more than 2. That's just some Grafana and Prometheus summing stuff. It consumed up to 2. And it's only getting about 1.48 itself, though. And while it's doing that, what happened? The pod with no requests at all looks like it's getting a tiny bit of CPU time, but it's almost starved. It's getting very little. The one with requests and limits is actually cruising pretty even at its baseline of 450 millicore. It doesn't really look like it was affected throughout this entire thing. And then 15 seconds over, that overconsumption ended. This blue pod went back down to 450. Interestingly, the one that had been starved actually started overconsuming for a minute. Different workloads will do different things, but note that this one was like, oh no, I didn't have any CPU. Now I'm overconsuming and before leveling out again. Interesting. I'll show one more thing and then explain what was happening. And the last thing I'm going to show is just do something similar, but I'm going to ask the one that has limits to overconsume. This one is limited to 1 core, recall. So in theory, it shouldn't be able to actually get up to 1.5 even if it tries, which it will try. All right, that started. And we can see on the graph something very similar. It's not going as high. It is limiting itself at right around 1, it looks like, during this period. It's still taking it away from this green one at the bottom, the best effort pod, the one with no requests and no limits. And after it finishes, that green one is kind of spiking again before going back to normal. That's the experiment. That is repeatable. It's fun in Minikube. So going back to why this matters, what exactly happened here? What was that behavior, and what can we learn from that or use from that knowledge to kind of inform what we do with our clusters? I'm going to start by deleting all of that because I'm going to be coming back in a minute, and I don't want those eating my CPU. Review. No requests, no CPU time during contention-ish. There's going to be an asterisk on almost every single one of these, by the way, because this stuff is complicated. I'm trying to keep it simple for 45 minutes. If you're using less than your request of CPU, it didn't look like there was any interruption. Not really, even during contention. You mostly got what you asked for. And for one of those workloads, when they got starved, it seemed to overconsume later. So that's kind of the keyword there is this is a compressible resource. If you don't get it now, you might get it later, assuming some is available. That might suck for your workload. It might not meet your service level requirements, but it will happen. So what's going on here? Diving down into kind of the C group level again, C groups is where all of the rubber meets the road in terms of how requests and limits actually are implemented in Kubernetes. C group and the completely fair scheduler is the Linux basically process scheduler, task scheduler, I'm not sure what the technical term is, that actually runs processes on the cores. And what it is a proportional scheduler. You can assign shares to any C group that basically say you have this much, this percentage share of the available schedule time in the event that you try and use it. Kubernetes equates, when it does this allocation, it basically says if you've asked for 1 full CPU, I'm going to translate that to 1024 CFS shares when I implement your container on the node. And Kubernetes is going to assign CFS shares according to the request that you made. If nothing else on the node is messing with C groups, this abstraction model can basically result in, okay, if you said you got 1 core and there's 2 cores available, that's 50% of the node that's kind of set aside for you. If anything else is making C groups, by the way, and assigning shares, all of this goes to, this is being recorded. It doesn't work. So, quick illustration. In the event that we assign, let's say that you're on a 2 CPU node, and you've got 6 total Kubernetes workloads assigned to this node. 2 of them have no requests, and the other 4 have some level of request. In this case, each of these will assume a number of shares relative to the number of millicores requested. Because nothing else is running on the system with shares, that has an interesting effect of it can actually consume up to, in this case, it's asked for 150, it gets 153 shares. It's actually going to be given priority for up to 284 millicore of CPU as long as these are the only processes running on the node. Because it's proportional. It's not actually about the number of shares of millicore you requested, it's about the proportion of shares you get on the node based on that request. So this is how the C group would kind of, or Linux would decide priority allocation for these processes. The other 2 that made no requests, there's an asterisk here. I literally learned during this conference that it's probable that Kubernetes assigns 2 shares to things that have 0 requests, which is really interesting, as opposed to a flat 0. There's a lot of hard-coded stuff, by the way, in how Kubernetes implements this that you just happen across. I'll mention some more later. Those 2 ones are basically what I like to use metaphorically as they're flying standby. If there's a seat available, if there's CPU time available, they'll get scheduled. They'll do great. We saw that early on when the node had 2 cores and only 450 millicore per process. If there's anybody that has shares is asking for those CPU slots, these guys get basically nothing. That's why we saw that one process that had no requests get completely starved out. This has implications for thinking about how do we assign requests specifically to pods running on a cluster, especially if we're like in Rafa's position and he's got to be telling all these developers what do you need to do. Oops. I'll get to that in a second. I realize I have a slide I forgot. But no requests means no priority, so be careful there. Limits are complicated enough that in a 40-minute talk, I wanted to put a QR code on the screen for an excellent article that talks you through kind of all of the interesting caveats and provisos that come with limits. They basically work. For workloads that are latency sensitive, there's some interesting implementation details that mean that they don't work quite as well as you'd hope, and you can get really poor performance from workloads that are being throttled as a result of the limits implementation. Limits are, again, coming from a C group setting, CFS quotas, but quotas are not evaluated continuously, they're evaluated at intervals. And if you exceed your quota at one interval, you might not get scheduled again until the next interval occurs, which is an unexpected lag time, hence latency issues, and so forth. A lot of cool articles about this. Those articles are all very long. The diagrams are all very complicated. For our purposes, what it really comes down to, though, at this level of talk is we learned that requests are pretty important. If you have no requests, you are basically flying standby. You do not get guaranteed any CPU time at all, especially in the event contention starts occurring on your node. And you're potentially subject to near complete starvation. If requests are all set, you're basically guaranteed a minimum amount of CPU time, the time that you requested. This has an interesting reflection on limits, because what that basically means is limits are often implemented to try and mitigate noisy neighbor issues where one workload could take cycles away from another workload. If requests are all set correctly, you're never going to be able to take away from a workload resources it has properly requested. So they aren't necessarily that critical for noisy neighbor situations as long as requests are set properly. A lot of people will argue and take the position that you just shouldn't set CPU limits at all as long as requests are working. And that's largely the side of the fence I land on, although I'm open to debate if anybody wants to talk about it. All right, so that's CPU. Could put a bookmark in all those memories. We'll talk, dang it, that was an unintended pun. We're going to talk about memory next before we kind of circle back and say, now we've learned a couple of things about these core resources. What do we do with that? All right, experiment number 2, resource settings and memory contention. So we're going to do the same kind of thing. I'm going to go back to the live demo. We still have this kind of observatory running, but I'm going to fire it up with some memory resource workloads. And these workloads I'm going to, well, let's just take a look. Applying a directory full of YAML, a couple of different services for 2 different deployments, one that has best effort, no requests and no limits, one that has some requests but no limits,
and one that has both requests and limits. Those should be running. They are. They are both running on the same node, so there is potential for contention. And let's take a look at the specific values they're requesting. We've got, again, best effort, no requests. We've got, for the one that has requests and limits, it's requesting 1 gigabyte of memory. And the next one down is requesting a gig and also limiting itself to 1 gig. This node, recall, has 8 gigs total. We'll start ramping this up in a minute. We'll get closer to 8. We're not very close right now. Let's run those. So I guess we'll go over here first and just take a look at what is going on, switch over to the memory namespace. Right now, the baseline consumption is small, so I'm going to bump that up. It's 85 megs each. Let's bump that up to something more interesting. Oh yeah, in case I wasn't there, I would go there, but I'm already there. I'm going to set it to about 500 megabytes on each of these workloads. In this case, I'm actually just restarting these things with an environment variable to set that baseline consumption. We can see that happen here. Tangent. One of the most annoying things to figure out in this live demo was how to make these queries for Prometheus show only the pods that were running and get rid of the ones that weren't, because CAdvisor keeps them around for about 30 seconds. Sometimes you can see the restart, sometimes you can't because the timing is that tight on the way the metrics work. In this case, you can't actually see them restart, but I guarantee you they did restart. First experiment. One of these things has a limit of 1 gig. What if we take it, this is the request and limits pod, or deployment, and we're going to have it consume an additional gig on top of its existing 500 megabytes for up to 30 seconds. I'll give this one away. It's going to get killed. It's going to get killed real fast. There that goes. Post request. Refresh this. It starts consuming just a little bit. It's that yellow one. And that down spike, that was it dying. But we can confirm that. We can observe over here. I'm going to take a look at the pods for that request and limits deployment. Note the one restart 13 seconds ago. And if we describe that pod, and I'm just going to grep for the container information here at the very end of the kubectl describe, we're going to be able to see a couple of things. No, I don't need to do that. Current state is started. That's great. The last state is terminated. Reason killed. Another bookmark, memory bookmark, killed. It told us exactly what happened. It was very clear. Love that. Doesn't always do that. We'll see it not do that probably in a minute. I say probably because there's some non-determinism here. Exit code 137. OK. Anybody surprised? Exceeded the limit. It got killed. Cool. That's like the easiest one to demo. I'm going to set up, just to demonstrate, the node has lots of memory. If you exceed your requests but don't have limits, you're not going to have a problem as long as there is memory, although we're creeping into uncertain territory here. So I'm going to ask each of these guys to consume an additional gig. This is the one that has no requests and no limits, and this one has requests but no limits. And visually, we should be able to see that. Here we go. So here's when we got killed. And then now we're having 2 of these pods consuming an extra gig, using 1.5 gigs each for the no requests, no limits, and for the requests but no limits. Just demonstrating that that works, mostly because it means containers running on your nodes can use as much memory as they want if they're not going to hit their limit, if the node has the memory available. So the next interesting question is, what if the node doesn't have the memory available? There's a lot of things that could happen here. I'll explain some of them later, but just to kind of show the simplest one. I'm going to change the baselines here. I'm going to change the one that has requests to request a lot more. I'm going to have it request 2.2 gigs and have it set the baseline to 2 gigs. So it's going to request a bunch and use some, but be within its requests. Should be able to see that. There we go. OK, it bumped up. Now it's at 2.1 gigs, again requesting 2.2. And I'm also going to set the requests for the one that has requests and limits. I'm going to bump its request to 5.2 gigs, set its limits higher at 6 gigs. That gets updated. It's not consuming yet because it didn't change its baseline. It just changed its requests. Just confirm that. So it restarted to get that new request and limits. Now we're ready. Now I'm going to start having it try and actually consume all that memory it requested. But this is going to put it real close to the node's actual limit of available memory. So it's going to try and consume an additional 4.4 gigs. So that started. There's actually 2 or 3 different things that can happen when I do this. It's usually one thing. We'll see if it's the one I expect, in which case my slides will match. But it has happened before that it isn't the one I expect, in which case I'll call it out on the slides. We're climbing, we're rising, we're getting close to the 8 gigs of memory that the node physically has available. And that was actually a lot faster than usual. What happened here? Suddenly, almost everything disappeared. Timing-wise, we can see that there was a slight, this no request, no limits pod actually did get killed. It got killed slightly before the other two, which interestingly, they got killed too. And looks like we're getting a restart now. So it took a minute, but those containers are running again. That's interesting. One of them's running again. Oh, this is, remember I said it's non-deterministic? This is actually one of the more unusual things that can happen. So there we go. Okay, now one of them's restarted, is using its baseline. There goes the other one. Okay, cool. All right, now we're back to the situation that I expected it to eventually get to. But basically, a bunch of chaos just happened. And yeah, there's only one node running in this cluster, but everything seemed to happen on the same node. And even though some stuff crashed, it stayed on the same node. We'll get to that. But first, I'm going to shut all these down. No, I'm not. I'm going to tell you something about them. This is why I write myself a demo script. There's too many commands. I wanted to take a look at that kubectl describe pod again and take a look at that container status. So we see again, the current state is running. The last state is terminated. Remember I said remember killed? This doesn't say killed. Interesting. But it is exit code 137, which, trust me on this, that's killed. All right, let's talk about what happened and sort of what that means. After, see if I'm right about, I think I do kill it now. Yeah, now I kill it. All right, there it goes. So, the review. If you have memory limits and your container exceeds them, it will be killed. At least that works as expected. Containers, unlike CPU, if a container doesn't get memory that it tries to allocate stat, something's going to get killed. Memory is not a compressible resource. You're not going to have that ability to just do it later in this case. What gets killed and how? That's the interesting thing from a cluster stability standpoint is there's not, if you start running out of memory, this is not great because you don't have a lot of determinism in exactly what's going to happen. So let's talk about what level of determinism you could have and why you don't always have some. Starting at the kubelet. So not Linux kernel at this point, but the kubelet. Best case scenario, if your nodes start running out of memory because workloads are misbehaving, they're over provisioned and the requests aren't quite being honored correctly, is the kubelet might notice. I say might because the kubelet's really only going to look for this kind of thing once every 10 seconds, and oftentimes in this overconsumption situation, 10 seconds is way too big a gap. Another fun thing is what kubelet's doing is it checks every now and then to see if the node's available memory has reached an eviction threshold. The eviction threshold defaults to something tiny. It's like 100 megabytes. If you're within 100 megabytes of having a problem, then it'll start evicting things. On modern nodes, that's nothing. I don't recall specifically what the various cloud providers end up having this set to. I don't believe they leave it at 100 megabytes, but it was interesting to try and experiment with on the defaults. In the event kubelet notices this, it will start performing evictions. Evictions are good because kubelet gets to decide what's the least important workload on this node. I'm going to kick you off, and you're going to go back to the scheduler and get sent somewhere else, probably not here, because I'm going to trigger a condition such as, did I say what it was called here? Memory pressure? I don't think I listed it. That basically says don't schedule anything on me, I've got some problems. That's not what happened in the lab. This was too fast. And I say probably because, again, there's some non-determinism here. Yeah, question. How does it determine least important? So there's a number of factors that go into that. A big one is quality of service. So we have guaranteed, we have burstable, we have best effort. Guess which one of those is the least important? If you have best effort pods running on that workload, they're probably going to get booted. There are other signals you can provide. Off the top of my head, I forget the specifics, but there's basically priority. You can assign pod workloads priorities, and those will also be taken into account in terms of what gets evicted. I don't think that I have used those a lot personally because, like I said, it rarely gets to this point on clusters that I'm familiar with, because what you usually get instead is you usually just reach killing, where kubelet missed its chance, the Linux kernel has stepped in, and it is just going to start taking over and killing things as needed. The interesting thing about determinism here is Kubernetes does its best with various cgroup settings to organize prioritization for the killer, but it doesn't get to pick. The Linux killer at the end of the day is what decides what to kill. Quality of service will have a huge effect on what gets killed first. Best effort stuff basically gets a signal, a prioritization influence to the killer, so it's at the front of the line. Burstable is after that, guaranteed is at the end. But killer also takes into consideration things like how much memory is actually being used by these processes, because my goal is to free up memory. So if it reaches that point, you don't actually get a total amount of control, especially with C group V1. I'll mention C group 1 versus 2 in a second. But in C group V1, there's only so much control that you get. And so if you get to out of memory, that's just bad. Yeah. Correct, yeah, so quick definition. A best effort quality of service pod means that it has not requested any resources and has not set any limits. Burstable means that it at least has requests. It might have limits, but if it does, the limits are not equal to the requests. To get to guaranteed, which is the highest quality of service, that means you're last in line to get killed, you need to request both CPU and memory, and the limits for CPU and memory also both need to be equal to the requests. You can't just do one, you have to do both. Which is interesting if you don't think that CPUs should have limits. It means that guaranteed quality service is kind of out of reach for you, unless you're going to lean into the over-provisioning higher costs. Anyway, we'll get there. So this is probably what happened in the lab. I wanted to highlight the fact that it didn't say killed because there's a bunch of nuance about what goes on. Long story short, there's some very detailed articles here if you're at all curious about what actually happened that go into detail. But you got to read what sounds like a PhD thesis or the actual code in order to find out like why in this situation does it not actually say killed. All right. So the last summary before we kind of talk about the last piece, that just going to wrap it up. Great, we learned something about requests and limits, but what do we do with that? Memory requests are also very important. Memory isn't guaranteed by request. One of the things I didn't emphasize in that lab test, everything was within its requested memory. Nothing was exceeding its request, but we still got killed. There's some things you can do to configure kubelet so that's less of a possibility, but requests don't guarantee memory, at least today. Because of the consequences, over-provisioning of memory has a higher consequence than over-provisioning of CPU for most kinds of workloads, so maybe we should be a little conservative on the limits there. Limits are more helpful for memory, mostly because it gives you more control over saying misbehaved workloads are the ones that should get killed and not the ones that are potentially minding their own business but have a noisy neighbor situation. Last note before we move to the last section, everything I just talked about is true when you are running on a Kubernetes cluster on an OS that uses cgroup v1. Cgroup v1, cgroup v2, it's the same basic system, a few differences. Cgroup v1 has some terminology changes versus 2 in terms of CFS. So CFS shares, like I explained earlier, is changed to CFS weight. It's exactly the same thing, basically, but different nomenclature. I found shares kind of confusing. I found weight less confusing. I don't know why they made the decision to change it, but that's one note. Memory gets new controls. Memory gets new controls that actually help you better say things like, if you are under your requests, you should not get killed. The killer should go after everyone else but you, which is not true on cgroup v1. So there's more determinism in v2 once we get there. I showed v1 because most of the major cloud providers aren't using that by default yet, but I get the sense that we're very close. Minikube is usually able to do that. So just a note on that. Finally, a call out to other kinds of resources. We talked about the abstraction. The abstraction is what Kubernetes is trying to present for lots of things. The built-in ones are ephemeral disk, memory, CPU. It's commonly seen these days to extend that to GPU, but it's a general model. You could, in theory, extend it to almost anything else if you wanted to, as long as you provided the implementation for it. I won't talk a lot about it right now because we're almost out of time, but just wanted to call out it is a generalizable abstraction. So, back to Rafa's story, like what do we do? Okay, we understand, we understood conceptually before that that over-allocation on nodes was gonna cause some pain. Now we have a little bit deeper understanding of what actually happens when that goes on. What do we do to try and influence our users of Kubernetes platforms to work on this, or what can we do to kind of maximize our stability and resiliency in our clusters in terms of resource requests? Sorry, it's kind of hard. As the ecosystem matures, there are other options, but we'll start from where Rafa did. Most people that I talk to about this, who've used Kubernetes for a while, they typically start with, I think I was actually talking to somebody before this talk, when you start introducing people to Kubernetes, you might not even mention requests because you don't need to set them to run a workload. So you might end up with a lot of pods in best effort. I think the guy, Tyler, on the talk before mine, Tyler specifically called it out in one of his slides. You end up with clusters all the time that have tons of best effort pods. so you don't bother setting them. But at some point, that's going to fall down. You might start getting some performance issues. Your cluster doesn't scale well. You realize you got to set something. Stage 2 at a large organization is you say everybody's got to set requests, but you know what? You don't have to think too hard. T-shirt sizing. You either choose small, medium, large, and that's good enough, and away we go. That tends to change when the cost pressures from that still ends up resulting in largely over-provisioned clusters. When the cost pressure from that comes down from the top, people typically advance to something else. Stage 3, manually tune every workload, whether, usually it's pretty irregular, and it's based on signals like, oh, this one's getting killed, or this one's getting throttled, or this one's showing up at the top of the list of the most expensive workloads in the company, in which case you should go take a look at it. But it's largely manual on stage 3. Through all of those stages, options that are out there to try and help your organization do well at this are basically, there were some excellent presentations. The presentation before mine did a good job of running over a lot of options for this. It's basically about creating policies, including policy as code, that can influence developers or application owners' behavior to guide people into paying attention like Rafa wanted to. He said he wanted to point people down the path of getting it right. There's built-in resources called limit ranges that you can use to ensure things always have requests, even if they're just kind of dumb defaults. There's resource quotas that can be used for if a group, like one of Rafa's customers back at the bank, had overconsumed themselves, they might be forced to stop and take a look at their allocation before continuing without affecting others if they had a quota in place just for their application. Tools like Caverno can be used to define much more granular and specific policies that, again, the objective is to influence user behavior on Kubernetes and kind of force people to invest time and effort in looking at their resource requests. If you're going to do that, it is really important to have some kind of tooling that helps them be successful with that. Even the little Grafana that I was running is something that can really help. Is you know that you're going to set requests according to what's actually being used, but you got to be able to tell what's going on. So any kind of tooling that actually helps people understand that would be pretty important. The last thing that we're seeing more recently, there will be a shameless plug for my employer at the end of this, is try and automate this. A lot of it are things that in theory, we should be able to have machines help us do, if not do absolutely for us. So how would that work? Ideally, a tool so the VPA, the vertical pod autoscaler, is an example. I would say it's not a very mature one in terms of its full set of capabilities, but it's an example of something. It should be able to observe and collect utilization data from workloads, calculate and generate tailored request settings for all of them, and then automate actually managing that in production. This article is something that is part of what forced me into giving this talk, honestly, was basically talking about the premise of the developer experience regarding it. It doesn't provide a solution, but it kind of talks about the problem more in depth. This is the shameless plug. The reason I get to spend all this time sort of digging into these details is I do work for a company that's trying to create exactly that sort of automation tool. We're not the only one. There are others. This is my favorite. So if you're at all curious of sort of other ways to do this, Rafa didn't have tools like this in his day. He had to kind of go the route of trying to influence his application owners and developers to do it themselves. But I firmly believe that whether my company Stormforge does this or somebody else wins out, or if there's an open source project that gets good enough, this is likely the future of resource management in Kubernetes, unless there's some insurmountable, intractable problem that I have not seen yet. Because there's way too many workloads. It's way too hard for developers to manually tune all of this, but it is really important for stability and reliability on clusters. I do think automation is where this will eventually end up. Not sure when we'll get there. With that, I've almost hit my timing. I don't think I've run over too far. And so feel free to connect with me on LinkedIn. I'm happy to. I'm a terrible LinkedIn person. I don't chat very often. I don't look at things, but I do promise to try and be more engaged for a little while after the conference if anybody does want to just talk about any of this stuff. There is also a link to, if you want to try my employer's free trial product, there's a link to that. And otherwise, we're open for any questions people may have. There's a lot that I didn't touch on, so feel free. If even the question wasn't directly addressed to something that I said in the talk, I'm happy to try and tell you what I think about it if anybody wants to go take particular direction. Yes?
Okay. See if this works. I was wondering if there's any way that you can provide back pressure to the process in the container to free up resources that it is using. So we have a monitoring pod that when it gets a lot of logs coming through it, it blows up and gets really big and takes up a lot of memory. But then when the traffic falls off, it doesn't free up its memory. It keeps it, you know, happy that it's got lots of memory. This is all within the limits that we've set. And is there any way to have Kubernetes reach in and say, garbage collect, you idiot? And
garbage collect, you idiot. I like that. So I'll mention first one thing that I'm aware of. I don't think it's a direct answer to your question, especially depending on the application, like if it's Java or something. One cool thing about the cgroup v2 implementation is there is an additional control where if a pod starts exceeding the memory it's requested, the operating system will start giving a little bit of pressure to try and free up some of that memory. I don't think that'll necessarily work for maybe, I don't know what the application stack was that your application uses. Say again? Vector? Sure, yeah. I am not aware of a Kubernetes mechanism to do that. If you didn't catch the talk before mine, that might be of interest. Tyler did an overview of a lot of tools related to this general idea of I want to do things like redistribute resources. He mostly talked about things on the pod level rather than the resources in the pod level. So I don't have anything that comes to mind myself, but there was some very interesting things in the previous talk. If you see it's ballooned to the limit. Yeah, okay, so if anyone's watching the recording, the question is basically, if we see it doing something, is there any way we can go in and sort of change its limits or requests and kind of force it to So when you say change limits or requests, my mind goes to the actual resources. There is a notable thing that's in alpha right now called in-place pod resizing. It doesn't get you what you want, but that's the only way to change limits or requests right now. At the moment, to change actual limits and requests, the pod is going to die. Like the pod has to get restarted. Right. Yeah. Short of general Kubernetes solutions like sidecars that actually just sit there and watch for things like that, I don't know of any tools that specifically would address that. It does sound like an interesting use case, though. Also an interesting idea of solution to go straight to, if it's over-consuming, let's just shoot it. I kind of like the aggressiveness.
Any other questions?
So for those of us who still have to do this manually, one of the things we discovered early on is, you know, when nodes start running out of memory, you know, things get unpredictable. Sometimes the thing that the kernel decides to kill is something important to the stability of the entire node. You know, rarely, but it would happen. So our solution to that was limit ranges have a feature in them. You can set the ratio of what the limit to request ratio is, and it can't exceed that. So we've basically made the requirement for memory requests must be the same as limits to prevent that kind of situation. Is that something you've seen other people do, have you seen other strategies to kind of address that kind of situation?
Yeah, so I think that's a great example of, it's using limit ranges specifically, but it's one of those like policy as code to kind of choose force people into a certain behavior. We have seen people who do basically exactly that, who just force memory to be have a 1-to-1 ratio. How they do it varies. Limit range is one thing. Inferno can do similar things as well. It's tricky because on the one hand, I say tricky because in terms of knowing when you need to increase well, actually, the more I think about it, there's not really any super downsides to that, except you're not going to be able to over-provision at all. But yeah, we have seen other people doing that, for sure. and that avoiding the chances of killing something important is a good call out, especially if there's any sort of non-determinism. It's one thing to kill a neighbor workload, but it's something else if you accidentally kill something critical to the system, like kubelet.
I was curious if you could, this might be a more basic question on Kubernetes, but you touched on like eviction, so when a process gets killed off and it gets sent over, I guess, rescheduled perhaps to another pod. Like how fast is that? Is Kubernetes like pre-seed all pods with all possible containers, or is there some memory copying that happens, like network transfer?
So working backwards, Kubernetes does not by default magically seed all pods on every node. It sounded to me like you're talking about like fetching images, like is it ready to start on another node immediately? Potentially no. There's absolutely no guarantee that it's doing that unless you've set that up yourself in your cluster. So if something gets evicted, from memory, I don't recall if it honors any sort of graceful, like does it give it a grace time as it shuts down to like gracefully close? It might not. So now it gets sent back to the scheduler. The scheduler is going to try and place it as fast as it can. That works as fast as it works for anything in your cluster. But yeah, if it lands on a fresh node that doesn't have the image, it could take a little while for anything that gets evicted to actually spin back up again. It's still better than just a random kill, but.
Any other questions? I can think of one. I see here that you've got a solution that tries to automate the setting the resource demands, but how does that work? Is it entirely based on assuming that future behavior will be pretty similar to past? A second question to that is there anything that solves the problem of, you're planning on having users give themselves their own labels for what the demands are? How do you keep people from being pigs in the organization and just saying, I want the max all the time if there's no cost back pressure on them?
Yeah. So again, working backwards, cost back pressure, especially in large organizations, most organizations that I've worked with who are like an enterprise scale do have something in place to do some cost back pressure. Some of the organizations I work with, though, especially if the organization has a lot of money and whatever they do is very important, like the best back pressure we've actually seen is, because typically the application owners are not the ones who are experiencing the pain of this. It's usually the platform owners. The platform owners are often just looking for any way to, as you said, give back pressure to the application teams. Oftentimes, it's just showing them that what they've requested, if to say how do we prevent them from like just asking for too much? One of the best ways is to have a clean and easy way of showing them that what they've requested isn't actually being used. Visibility, transparency is one of the only things you can do if there's not any other direct costs there. But we're kind of talking about a people problem now as opposed to a technical problem, which working backwards on your question again, the people problem thing. I think automation tool, in terms of like how does an automation tool handle this, I want to call it first that the objective is to reduce load on people. And so an automation tool is typically going to work pretty well for like 80% of workloads. There's likely to be a few workloads or a few circumstances like Black Friday's coming up, and there's no way that we could have predicted that by looking at the last 2 months worth of data, where somebody's still going to have to step in. But any automation tool's job should be to try and reduce the amount of work that people do to only exceptional circumstances as opposed to everything. The way that our particular tool works is it is we observe about a month's worth of data every time we generate a new recommendation. There are some ML algorithms that do have forecasting and concepts of seasonality. They can tell that your workload is busier on Monday versus Saturday and stuff like that. But outside of you'd have to have user inputs or policies that say things like this workload needs to be as reliable as possible versus this one you can maximize for savings. It's a complicated, it turns out the answer to your question is slightly complicated. But an automation tool, in addition to just forecasting, ideally should be responsive. It should address things like, oh, this thing just got killed 5 times in a row. I think it might need something new, even if its forecast, its previous data didn't show that. I think you might have asked more, but that's all I could remember.
Okay, last call. We might have time for one more question if there is any. If not,
One thing you just briefly touched on was auto-scaling. And I could imagine a scenario where with requests and limits, you're sort of restricting supply, but of course the horizontal pod autoscaler is going to try to increase demand based on possibly a different set of metrics. Seems like you might get, just maybe you could comment on how autoscalers and
Yeah.
those things kind of work together.
So autoscaling, and specifically horizontal pod autoscaling is what I'm hearing, because there's 3 different core means of autoscaling in Kubernetes. Yeah, so what we were just talking about is the individual requests and or limits for a pod, but when you have a horizontal pod autoscaler in place, its job is to try and make the utilization, oftentimes, there's other metrics, but oftentimes match some ratio against the requests that have been configured. In the event that you want to do multiple things, where you want to say, great, I want the horizontal pod autoscaler to be working, but I also want to pay closer attention to this individual pod's resource request and or limits. That's I think mostly what that keys, the first place my brain takes me is remember that the VPA project, kind of the existing standard public one, specifically states that because of potential tension there, like it doesn't play nice with horizontal pod autoscaling. You pick one or the other. You don't have to. Commercial products, the ones including StormForge and I'm sure others, do vertical pod autoscaling in conjunction with horizontal pod autoscaling. It's an interesting problem because either you just preserve the shape of the existing behavior when you start vertically sizing pods, in which case you have to adjust the horizontal pod autoscaler's targets, or you have to start getting a little bit more, now I'm speculating as opposed to talking about built software, or you have to start changing what those metrics are depending on the number of pods running. Like maybe if there's more pods running, you're more okay with having those pods more saturated, as opposed to if there's only a few running, you need to have more overhead. Mostly, I think what that all that response tells you is that that's a complicated, interesting question. But you knew that.
Okay, thank you, Reed. That was a great presentation. Please join me in thanking Reed. So this evening, we've got a couple events. There's a general audience game night starting at 8:30. If you brought your family along, that's in the exhibit hall, but if you brought your family along, the first hour is deemed family hour. There are games for kids there starting right now. If you need to stick around until the adult game night starts for another hour, there's a session on how to volunteer for SCaLE. I don't recall the room, but I think it's in the other building. And then at 10 a.m. tomorrow, Casey Hanmere, who's a physicist scientist with Caltech and JPL, is giving a general talk that sounds really interesting on technology opportunities. So thanks for attending today. Maybe I'll see you at game night if you stick around.
I think there are some compressed options, and just so it doesn't bounce, you might want to send a compressed option.
Let me go check the name real quick. I should have mentioned that because I figured somebody might be interested.